double check.
All right. Hello, everyone, and welcome to day 2 of the UIF-CW. Thank you so much for being here in person and virtually. So my name is Alika Srinivasan, and I'll be your MC for today. I'm a William M. LaPenta intern with the EPIC program. And I'll be your MC for today. A crucial part of my role as your MC is I must ensure time management. This is to respect the tight schedule and provide equitable speaking opportunities for all presenters. I apologize if I may need to gently alert or interrupt anyone, purely in the interest of fairness and timekeeping.
My coworkers, yep, it's off. Gotta save that battery. There we go. Sure, it's actually gonna work decently though. Not a fan of that delay.
Okay, so there's a delay.
There's a slight delay.
Okay.
Longer. It's much longer than I'd like. Feel about that? I can try to figure. It looks like it's a little bit quicker sometimes. There's a little bit. There's maybe for some reason the first one to the second one is the longest,
Okay.
and then it gets a little bit better. I can try to figure out a different solution, but that probably won't be until lunchtime.
Yeah, we gotta get started.
Figured. Better like this, but I really don't want to put you in that situation.
Okay.
It's like, oh my goodness.
Is it like Bluetooth? Is that?
It is Bluetooth, and there's a lot of people in here, which kind of, you know, connection.
Okay. We can just leave it there. Okay. Good morning, everyone. So today I'm going to do the welcome and kickoff. My name is Jessica Wheeler, and we're going to go through the day and see what the day looks like for the agenda. So today's moderator will be Akila Servan. Unfortunately, she can't be in 3 spaces at one time, so I'm taking over for this session. And so we're going to go for today from 9:05 to 10:30. We'll have the parallel sessions, which are happening right now. And then we will have a break at 10:30. At 11, we'll have a continuation of the parallel sessions. And then at 11:30 to 12, we'll have a Q&A for these sessions. And then at 12, we'll break for lunch. And then also, I wanted to mention there's an opportunity to actually meet Alikia in room 2126 during lunch, if you're interested. After we come back from lunch at 1 o'clock, we'll all be joined together in the main session room with community discussions with insights from industry and academia, followed by a panel discussion on use cases and needs of UFS applications and new professionals and professors in industry. Then at 3, we'll take a break. At 3:15, we will have the next set of parallel sessions on cross-cutting concepts, and then we'll break at 4:45. And then our last session for the day at 5, we'll have a joint Q&A session on those parallel sessions with cross-cutting concepts. So just a reminder, we are live streaming this event, so please be aware of hot mics and video recording. If you would like to be further from the microphone, we suggest sitting towards the back of the room. Also, just another reminder to connect with us on social media Twitter as well as Instagram. So these are the Twitter handles as well as our Instagram name. Also, if you need to connect to Wi-Fi, that can be found on UCAR Visitor. That's the name, and there is no password. Also, this is just a QR code for the event guide. It is a lengthy event guide. It's about 150 pages, so feel free to scan that QR code, and it'll give you all the details for today. Thank you, and now I will bring up Curtis Alexander.
Oh, yeah, that's fine. Thank you, and welcome again, everyone, this morning here for the short-range weather convection allowing modeling rapid refresh forecast system session. Look forward to a great amount of presentations, discussions here over the next, well, 3 hours, including the break. So we do have a packed agenda. We're going to ask presenters to try to keep their presentations to about 10 minutes in length if they want any time for questions. We've got about 12 minutes total per presenter, 7 of them before the break. So I want to get right to it and welcome our first presenter, Matt Pyle from EMC. He's going to be giving us a presentation here on the current state of NOAA's Rapid Refresh Forecast System.
Obviously, I'll be speaking on behalf of my co-authors and also speaking on behalf of the wider RFS team, which is spread across mostly GSL and EMC, but also brings in inputs from the wider UFS community for certain aspects. What is the RFS all about? A big picture item is the unification of the convection allowing models, going from the HER, NAM-NEST, and HIRAS window, running over a number of small domains with multiple dynamical cores, kind of trying to boil it down to a UFS-based system based on the FV3 dynamical core running over just a single large North America domain. A key aspect of the RFS system is the DA system, particularly the hourly DA cycle, which includes a 3-kilometer ensemble for hybrid 3D ENVAR. Forecasts are made to 60 hours every 6 hours, so the main synoptic cycles, that includes both deterministic and ensemble forecasts. And deterministic only forecasts are made to 18 hours for the other cycles during the day. The physics broadly match the HER. And just sort of stressing the bigness of this thing on the final bullet. It's intended to subsume all products and functionality from the HER, NAM-NEST, HIRAS window, and href. Okay, so digging into the data assimilation a little bit, we have the ensemble system on the top with the green boxes. Those are the basically 30-member, 3-kilometer ensemble. Those are stepping forward each hour. We have the deterministic system in the circles below it, also stepping forward each hour. Have the ensemble information feeding into the deterministic analysis and at least a certain amount of recentering from the deterministic analysis, recentering the ensemble. Then at the bottom is this, what we call the partial cycle, where we bring in fresh GFS information twice a day. That's just to bring in sort of long wave information outside of our domain. It's something that's been used in the RAP and the NAM for a long time. And while it brings in fresh atmospheric informations, the land states are fully cycled. Planned additions for the RFS system going forward in the sort of in the near term. Multi-scale DA, which I'll go on the next slide. Also want to add modeling of small lakes. This is something that's done in the HER. We want to bring that in for the RFS as well with the CLM lake model. And the last item I call sort of a maybe item because it's still being evaluated to make sure its sort of scientific integrity. But that is to go to 32-bit physics, which would definitely give us some breathing room on the computation side of running this huge North America domain. Multi-scale DA, in the interest of time, I'll just focus on the second bullet and the idea that it allows for all observations to be assimilated at once. Instead of having the radar data assimilated separately as a second step, it's all done at the same time. And the big take home, the big benefit we're seeing from this is an improvement in the balance of the analyses, sort of as measured by the mean absolute pressure tendency. About 40% better with this approach. Jumping into just a little bit of verification, these are deterministic 12-hour forecasts for the May and June period, 2-meter temperature and 2-meter dew point. We have the RFS in red, the HER in blue, RMSE solid bias dashed. Focusing at 2-meter temperature on the top, you see that the RFS lags behind and is significantly worse sort of in the late afternoon and early overnight period. Sort of coincident with the RFS having a sort of a strong cold bias. This is something that's we're looking to understand at this point. 2-meter dew point's a little bit better story with the RFS generally as good or better in terms of RMSE, and curiously sort of a flip in the diurnal cycle of bias. Okay, 24-hour QPF for the same May-June period. Same colors, and we have equitable threat score, sort of skill on the top and bias on the bottom. But for equitable threat, we see the RFS really lagging behind, especially I would say between say 1/2 inch and 2-inch thresholds where it's significantly worse than the HER over this time period. On the bias side, we see that the RFS is higher bias than the HER and gets up to a sort of a concerning bias of about 3 for the 3-inch threshold. And this high bias is sort of a long-standing RFS FV3 issue over the last several years, mainly an issue during the warm season, and it also manifests as a high bias in higher reflectivity values, overly intense, overly large storms. It's been a more focused effort to look into this issue and try to address it over the last year or so. This has led to the exploration of a variety of approaches. I've kind of broken them down into what I call the less scientific and more scientific approaches. Looked at some damping possibilities, basically the damping of condensational heating, capping of the microphysical heating tendency as used to be done in the HER. These things helped, I would say, a little bit, but definitely weren't the magic bullet for solving the problem. Also looked into some more scientifically based approaches. Done some work on looking into revisions to the physics dynamics coupling, but I think we decided it wasn't going to be ready in time for the RFS version 1, so kind of shelved it. The other thing that's still being looked at is the inclusion of Grell-Friedis deep convection. An example courtesy of GSL where we have a run without Grell-Friedis on the left, run with Grell-Friedis on the right, and the MRS OBS in the middle. Two things I want to point out from this is the no GF run basically has overly heavy convection over sort of southern Texas, which the run with GF kind of cleans up. In the more concentrated region of convection, say over Oklahoma, the GF scheme definitely changes the answer somewhat, but I'll say it doesn't completely wipe out the convection. So this is sort of why it's we've been encouraged by some of the first stuff we've seen with the GF scheme. Okay, the forecast ensemble. I feel like this information on this slide has become dated since I submitted my slides. The original plan was for a 12-member time-lagged ensemble. There's been more recent discussion, especially if we can go to 32-bit physics to run more ensemble members at each cycle. And instead of just using time lagging with the current member in the previous cycle to maybe consider the 2 previous cycles, maybe get the membership up into the 20 to 30 members, but that's still being investigated or thought about. Other question is single physics versus multi-physics. The long-term plan is definitely to get to single physics to be unified both in dynamics and physics. However, we've sort of left open the possibility of multi-physics for the first version just to enhance, as a way to enhance spread. Both of these options were considered or evaluated during the 2023 spring forecasting experiment. And to say, I think the decision officially still has to be made for the initial RRFS. As we'll see, the options show differences in sort of the skill spread reliability space. Okay, this is also sort of from the May-June period, basically with the single physics in red, the multi-physics in blue, RMSE solid line, and the spread with the long dashed line. Basically for all of these 2 meter temperature, 2 meter dew point, and the 10 meter winds. The multi-physics has both higher spread and higher air, probably not unexpected. Though somewhat concerning is the 2 meter temperature, which shows dramatically worse 2 meter temperature with the multi-physics and a pretty pronounced cold bias by the end of the forecast. Okay, on the sort of reliability side, looking at simulated reflectivity reliability at different thresholds, with the ideal being on the diagonal of the plot. Pretty much all of these examples, multi-physics in blue is somewhat more reliable, somewhat closer to that diagonal perfect reliability. However, in both cases, they're all sort of overconfident or high biased in their probabilities. Okay, so in quick summary, just say that tremendous progress has been made on the RFS over the last couple of years, if not longer. But work still remains to be done to a place where stakeholders will be comfortable with it, replacing a huge swath of models that forecasters are used to. The high precipitation bias and sort of a inadequate RFS ensemble performance on day 2 in particular, which was noted in the spring forecasting experiments results, are 2 critical items that we must improve upon. And we have been targeting a late 2024 implementation for this first implementation of RFS, but addressing these sort of big science issues is likely going to push it back into 2025. And if we have time, I'll take some questions.
I think for the sake of time, we're going to keep going to the next presenter. We can come back out chat as well for remote attendees. So we're going to move on to our second presentation, which is going to be remote. This is going to be from Israel Murak at SPC. I'm going to be reviewing the evaluation of the rapid refresh forecast system, the 2023 spring forecast experiment. So do we have Israel remote?
Yeah, Curtis, can you hear me?
Yeah, we can hear you. And there we go. You'll have to, just so you know, Israel, the projector in here is losing its ability to display color. So we'll just have to live with that for now, and just understand there may be a little more ambiguity on the our end of the presentation. So, but I'll let you take it away. Thanks, Israel.
Yeah, thanks, Curtis. Thanks for the opportunity to present here. I acknowledge co-authors here, Adam Clark, David Harrison, and Jake Vansel, on putting these results together from the HWT spring forecasting experiment. So we evaluated, this was a period May 1st through June 2nd. I'll note that this was a below average period of severe weather climatologically. I'm going to present results, first start with deterministic and then ensemble comparing RFS to the operational baselines. So we'll focus on the subjective evaluations, so there's some objective evaluations thrown in here. And these are just to note over a mesoscale area of interest for each day where the severe weather threat was the greatest. So starting off with deterministic, this is an evaluation we did with looking at the DA, so the first 6 hours of the forecast. And we see in the 1 hour forecast that HER had higher subjective ratings in terms of forecast performance than the RFS. Also for 6 hour forecast, but the differences were a little smaller. The noted participants noted that the RFS had a high bias in intensity and coverage, kind of things that Matt talked about just a bit ago. And here's just an example. I'll show the May 9th derecho event and several examples here. So this is the 1 hour forecast from the 10th 0Z cycle, her on the left, RFS in the middle, observations on the right. And you can see this high bias and reflectivity. There's some 65 dBz cores in the RFS 1 hour forecast that are much weaker in the leading convective line of the MCS in that at that time. And also there's a lot of spurious storms that pop up that aren't in OBS or the HER 1 hour forecast. So those are concerns. Obviously, those storms continue. It sort of eats away at the instability and can degrade the downstream forecast of those types of scenarios. Shift gears to the full day 1 results for the 0Z cycle. Here, comparing the HER to the RFS. Below this 0 line here, the RFS is slightly worse. Above it's better. So for reflectivity and updraft speed, the 10-meter wind, convective winds, where things looked a little better for the RFS. And again, the comments from participants in these ratings were that the RFS developed storms that were too intense and too numerous or widespread across the domain. And here's an example. This is probably one of the poor forecasts from the RFS. This is a 0Z forecast. It's a 20-hour forecast of the derecho across northern Kansas. You can see the RFS doesn't really have any convection. It's farther back to the west. While the convective mode isn't perfect, it's a much better representation of what was now a significant severe wind-producing MCS across Kansas at this time. For the 0Z environmental fields, again, edge to the HER for Cape, temperature, and dew points, with the Cape field being the most commonly favored in the HER over RFS. Oops. We also did a blinded evaluation, so no labels on the models. We called it flagship because the centers produced provided their best deterministic run. So we had the HER and RFS, green and red. So you can see, just comparing those two, statistically significantly higher ratings for the HER over the RFS in this blinded 0Z model evaluation. NSSL had some impasse runs. Notice that was actually slightly higher rated than the RFS for the 0Z. Then GFDL had their FE3, and NASA provided their GEOS FE3 as well. So again, if we shift gears to the 12Z run, we see different results. So this is pretty interesting to me. Things become much more even in terms of performance when you look at the 12Z cycle. You can see the distribution sort of centered on this models being about the same for HER and RFS. And if we look at some objective verification in terms of 40 dBz reflectivity, that actually shows up here as well. We, again, over our domain, our area of interest, the RFS and HER, very similar performance characteristics for the 12Z cycle. So found that to be really interesting, encouraging. As Matt said, these have very similar physics. So they have very similar performance characteristics. Now, this is, again, the 12Z run. We haven't done the stats for the 0Z run. I'd like to see if there's a bigger difference like we saw in the subjective evals for the 0Z. And just as an example, again, this May 9th derecho case, RFS 8-hour forecast now is much improved. In fact, it's better than the HER forecast here. So there's something about the 12Z runs during the spring period where the RFS was much closer in terms of performance to the HER. In terms of ensemble evaluations, we compared the RFS ensemble to the HRAF. This is looking at the single physics ensemble. Again, same orientation. If it's below the 0 line, RFS is worse. Above, it's better. So for updraft helicity and updraft speed, there's slightly favored the HRAF over the RFS for the 0Z cycle. 10-meter winds and reflectivity was more similar. Here's again an example of what we looked at. We looked at these neighborhood probabilities and overlaid reports. HRAF on the left, RFS. So the participants generally rated the HRAF as slightly better on this day, better orientation of the higher probability axis, better centering of the higher probabilities as well. For middle field 0Z runs, again, slightly favoring the HRAF, 2-meter temperature, dew point, and Cape again. For 12Z, we see a different story. We again see more similar performance characteristics. These are the subjective evaluations. We see pretty similar distribution of ratings for these 12Z cycles. So again, somewhat different performance in terms of 0 versus 12Z cycles. If we look at some statistics, this is again of our domain of area of interest, 40 dBz, the rock area, pretty similar. HREF, its biggest advantage here is that 10% probability has higher POD and lower FAR. So just a little broader expanse of the lower probability that catches more of the observations, the 40 dBz echoes. And reliability diagram, kind of what we've seen historically with HREF, just produces a more reliable, or at least closer to a reliable probabilistic forecast, especially above 30%, compared to the RFS, which tends to be overconfident throughout at all probability thresholds. If you dive into some of the member performance differences, you see some interesting things. First off, just want to acknowledge that there have been significant developments and improvements in FV3 because the starting point was down here, this high-res window FV3, and notice now the RFS controls up here. So several years of development, sort of a worst to first performing deterministic run. So, we certainly need to acknowledge the improvements that have occurred with FV3 and convective forecasting. If we look at some other, this is comparing HREF members to the RFS. You can see the RFS control and the HER sort of stand out as best. The high-res window ARW is a sort of a next tier performer. And then there's a lot of models clustered here. The perturbed members, single physics members, the NAM-NEST, Nissel-Whorf, and then the high-res window FV3 kind of stands alone as the worst performing deterministic run. When you look at sort of how they cluster together, you can see these perturbed single physics members, very similar performance characteristics. So at least in terms of performance, not much difference there. They certainly lag the control member. Notice though in the HREF, this darker blue dot circles here, much different performance characteristics for the HREF members. I think that's, identifying the diversity and different performance that you get from the HREF configuration. And then the lighter blue are all the HREF time lag members. So even though they're lower performing, and you can see that basically 7 of the HREF members individually are worse performing than any of the RFS members, yet the HREF ensemble provides more skillful and reliable probabilistic guidance. So kind of an interesting thing to think about how you can get a better ensemble out of worse performing members. Shift gears now, focusing on RFS configurations here. Single physics in orange, multi-physics in purple. You can see in the subjective ratings, very similar distribution. So we really didn't see much difference, and I individually went through each individual forecast, and they were very similar day to day. Statistically, for 40 dBz reflectivity, again, the ROG curve, very similar. Reliability, pretty similar as well. If anything, it's maybe a slight edge to the single physics here. If we dig in a little bit to the member performance, you can see here the stars are the single physics members, and now the circles are the multi-physics members. And you see sort of this clustering. So basically, you're seeing better performance in the MYNN Thompson physics suites compared to the circles here in blue are the GFS EDMF PBL scheme. So basically 6 of the 10 members in this multi-physics ensemble were this clustered, poor performing GFS PBL members. So we're sort of hypothesizing that, just including more than half the members here, poor performers, that you're sort of artificially degrading the multi-physics ensemble performance. In terms of time lagging, those are highlighted here. You can see those all performed similar to one another, but they have lower ratings overall than the HREF and the single initialized ensemble, time ensemble from the RFS. And then lastly, wrapping up here, the day 2 performance. This was probably the biggest surprise from our results during the spring, was that the HREF had a much higher rated subjective forecast for the day 2 period than any of the RFS configurations. Notice those are all here to the right, and they are all pretty similar, but much lower rated than HREF. So was that an artifact of the type of weather we were dealing with, or is that a real signal in the forecast performance? So to summarize here, just highlight that there have been major strides in FV3 modeling at cam scales over the last several years. 0Z HER was rated as performing better than 0Z RFS, but kind of surprising, the 12Z runs were much closer in terms of performance. So there's something about the the initialization time that was different during this past spring. And despite poor performance from members in the HREF, the probabilistic guidance is still more skillful and reliable than the HREF or RFS ensemble, which, as we know, tends to be a bit under dispersive. The RFS multiphysics ensemble did not appear to be optimally configured because of the majority of its composition being poor performing members of the GFS PBL scheme. The time lag RFS ensembles were rated lower on day one than the ensembles initialized a single time and the HREF, so that's a concern if we're going to rely on time lagging. And then for day two, the HREF forecasted out as much higher rated than the other RFS configurations. So if there's time, I'd be happy to take questions.
Thank you, Israel. I think we're going to keep going here. Like I said, if you've got questions, you can save them. We're going to have plenty of time for Q&A after the break this morning. And then also, if you're remote, you can put them in Slido, and we'll capture them there. So we're going to pivot to our next presenter, Lou Wicker from NSSL. And he's going to be talking about assessment of convective scale attributes of the Fe3 dicore using idealized simulations. So, Lou, take it away.
Okay, so I just... Dun, 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 there it is. Somebody bringing it up? Okay, there we go. Okay, this, if you were at the NWP last week, this talk is apparently snake bit for color too this week. Last week was something else. I'm going to change gears a little bit and go to more of a theoretical discussion, trying to understand some of the attributes of the Fe3 dicore. And a lot of people have helped me with this. Their names are here, and I've probably missed some people. So I'll just kind of move on here, assuming I can actually run this weird keyboard. Let's see, page down. Is it just, okay, now I did it. Exactly. So, no red. Okay, so I have a lot of red in these slides, so this isn't going to work really good. But the top, I just want to talk about the top line. One of the things about NSSL's view or way we look at the world is because of our Warn-On forecast system, we're focused on predicting the individual behavior of the behavior of individual cells. And that means the details of the convective structure, if they're rotating, the evolution are all important. And so the model output needs to look like the radar. So we're very focused on the details, just like the forecasters are. Okay, this diagram I'm going to go pretty fast, and I did that. Okay, nobody else had this problem, but I am going to have this problem. All right, so what I did, we all know Fe3 has a high precip bias. And what I was able to do, what I've worked on for about the last year, is to take 3 models, actually 4 now with MPAS, but I'm not going to show that here, and set up some idealized squall line simulations with just Kessler microphysics, because Kessler is simple enough you can actually check the code and know that you're getting roughly the same answers. And then I put in different shears and different capes. This is a low shear case, 6 meter with 6 meter per second over 2.5 kilometers. So it's a sort of a upward tilting shear squall line. This is what they look like if you run it out for 4 or 5 hours. The sort of grayscaled stuff is, yeah, everything looks black, great. So the grayscale stuff in the back is a cold pool, and then the blobby stuff is actually what we call the updraft objects, which is a criteria where you look for reflectivity above 35 dBz and updrafts above 700 millibars, greater than 5 meters per second, and anywhere that's created. So this is kind of what they look like, okay? There's obviously differences here. So when you look at those squall lines, the question you have is, can we reproduce the behavior in the we see in the real data cases? And the answer is, amazingly, yes. Here is the 95 percentile time series of precip, and the top line, the weird gray-green thing, is RRFS, and with the circle on. And this is this is just the top 15% or 5%, and we're already at 50 millimeters in 15 minutes. So we have these really intense precipitation bursts. They do occur early on. CM1 and WRF down below do as well, but we're going to look at this sort of en masse now. Yes. So we'll do a kernel density estimate, and now we're looking at 3 different capes, or 2 different capes, 2,000 and 3,500, and a couple of different shears, which is kind of spanning the space of my squall line runs, which have a variety of different combinations. And what you see is in the low shear, low cape regime, that you have this incredible tail that you can't actually figure out because it's supposed to be red, but it's down there where that almost 80 millimeter line is, and that's the FE3. This is the FE3 solo core, so it's not quite the main core, but it's taken from the GFDL repository. CM1 and WRF, let's see, do I have a mouse here? No. As you go up in shear, so you see this very long tail, and in fact, all the FE3 runs have this very long tail. It's the line to the right, okay? But as you increase the cape, things get closer, and then as you increase the shear, they get closer still. So two things here. One is that the idealized squall lines with the FE3 RRFS, and these are all, the RRFS and these models are sort of configured with 3-kilometer resolution. The vertical levels are actually the operational vertical levels, things like that. We're trying to make everything sort of look like the operational runs. Basically, the Kessler schemes can actually show the behavior that we seem to see in the real data cases, and then that is also a function of the environment. So this is this object methodology I just described a few minutes ago, where there's a CREF, 35 dBz, and then the W, and then this is the objects we get. And then we can average quantities over each object. For example, we can look at the size of the object, or we can look at the vertical profile of W within that object, and we're going to look at those things. So again, this is kind of hard to see, but this is what the objects look like at 2 hours and 4 hours for the different runs for the weak shear case. And you can see there's a definite difference in the object sizes and shapes, and we can quantify that by going to a list, counting the pixels in these objects. Come on. All right, there it is. And you can't see it very well here, but the FE3 is the farthest to the right line everywhere. So there's some MPAS results on here, but the basic idea is that at the 90th percentile, the size of the pixels in the WRF and the CM1 are about 8 for the low shear case, whereas in the FE3 they're 15. So they're much bigger objects in the FE3. So this is very much like confirming in my mind what people see visually, that we have these very large, intense cores, which are also associated with the rain. Again, it's a function of shear, but all the time, you know, the farthest to the right line here, the red line, is the FE3. So we now sort of established we have these large objects. What's going on inside these large objects? On the upper left, or on the far left here, is just what started this process several years ago, where the operational models, HER, RRS 1 and 2, which was really the NORD tests, where we were going from the 6th to 8th order divergent damping, had these very much stronger updrafts and very much deeper updrafts, kind of like the NAM did. And the HER is the black line on the left side, and the dashed lines are the RRFSs. So in our idealized setting, we basically go here, and what we have seen over a lot of different experiments and a lot of different configurations, the FE3 updrafts are deeper and than the CM1 or WRF updrafts, and that's the sort of inside line that goes up, and now the equilibrium level is about 1 kilometer or 2 above the other two models. So one question I have always is, why are the updrafts deeper? The other thing we sort of have worked out, God, this is irritating, is if you go just to the 1 hour, which means the first initialization, the updrafts are really strong in FE3. There's this initial burst, and in fact, it's really, really intense. The FE3 here is the farthest to the right line. It's almost twice, I wouldn't say it's twice as long, but it's strong. It's pretty darn strong. And that's associated with the precip bursts that you see on the upper right-hand side here. So you can sort of connect the precip to the updrafts here. So the question then becomes, why are the updrafts stronger? And thanks to my colleague, Christiana Janabalaski, she sort of keep looking at the divergent damping. She's been after me for 6 months on that kind of stuff. And I went back and I put horizontal divergent damping, not acoustic damping, which would be both horizontal and vertical, into a toy cloud model that I've had for years, where I've tested a lot of schemes. And what I did was basically configure it with no shear, but 3 kilometer and the horizontal 200 meters, and basically vary the horizontal divergence damping. And I went and implemented 4th, 6th, and 8th order horizontal divergent damping, and used the coefficient that's used in the operational version for the FE3. It's hard to see because we've lost color, but I will say this, that except for the fourth order, the sixth and eighth order actually produce stronger updrafts, and the sixth order is about maybe a half kilometer deeper in this toy cloud model than the sort of control run with the acoustic damping, which is not only damping the sound waves. So we can actually reproduce the behavior we see in those profiles in this totally different model. It's a C-grid model. I mean, it's just, I was kind of amazed this actually worked the way it did. So what happened, how do we test? So we went back and I tested this in the FE3. The horizontal divergent damping coefficient in the FE3 is maxed out pretty much. You can't really increase it. So I had to decrease it. And what do you see when you decrease it? Well, the farthest right line here again is the sort of control version, but when I decrease the FE3 coefficient for the divergent damping by a factor of 2 or a factor of 4, I now cut the updraft back by about 40%. This is at the low shear case, and at the higher shear case, like we said, there's not as much difference. Other processes, entrainment, pressure gradients, all the sort of two-dimensional dynamics that you see in squall lines are probably sort of keeping things a little bit more the same. So the basic takeaway here is that the horizontal divergent damping is reducing the value of the two-dimensional divergent damping reduces the updraft intensity. So there's a magic bullet, right? You can do that, except that as soon as you start, because you're on this numerical grid that they've chosen, oh, no, there's another one in here. Oh, you're kidding me. This is the wrong slide deck. Okay, hang on. I think it's in here at the end, and then I'll finish. Well, I have a bunch of reds, so it doesn't really matter. It's probably hard to see. I had a better figure made up. But the surface pressure field here, if you reduce the D4BG on the things, you start getting grid scale noise when you reduce the divergent damping coefficient. And that's the same thing even aloft in the middle of the storms. So you can't really turn things down to fix the one problem because you're going to create this other problem. So in conclusion, if I have time, Curtis, if I can go back, okay. The precipitation differences seen in full physics runs can be reproduced in a simple setting. This conclusion I come to, and I think I've demonstrated it pretty solidly here, is the underlying dynamical core design is the problem here. And despite FE3's designers' best efforts, well-intentioned efforts, using the D-grid for the convective scale prediction, which is really what essentially you're doing when you're looking at the divergence and the pressure gradient, is that you need a large amount of two-dimensional divergent damping to stabilize the model solutions. More filtering leads to larger storms. Paradoxically, it appears that two-dimensional divergent damping, an excessive amount, creates deeper updrafts that initially can be very explosive and intense, producing the large and intense precipitation rates that you see in the model. Full mitigation probably requires rewriting a new dynamical core, and then we can discuss later cost-benefit of building versus adopting. And I want to say, I don't have time obviously to show this here, but a version of the NSSL's FE3 warn-on forecast system, we built that with FE3. But the imbalances of rapid cycling, 15-minute cycling with radar and satellite makes the solutions very noisy, very difficult to control. And we're doing 15-minute cycling over 6 or 7 hours before we're producing forecasts. We do it for actually 12 hours. So we really can't use a model that takes a long time to settle down or requires a large amount of dissipation in order to control the grid scale noise. So basically, we basically have decided that we cannot use FE3 for WAFs, and we're basically moving on to another dynamical core that looks like it has a more bright future. Thank you very much.
May have died. Oh, there we go. Okay, so we're going to switch back to online presentation from University of Oklahoma. We've obviously now had 3 presentations focused on modeling at CAM scale related to the RFS, the overview, as well as real and ideal evaluations. We're going to talk about data assimilation for the next few presentations, and we'll come back to modeling before we get into our discussion session. So this is going to be Yu Yang from University of Oklahoma talking about convective scale background error covariance and hybrid ENVAR for radar reflectivity data simulation. So take it away.
Thank you. Thank you for the introduction. I'm going to talk about the convective scale static B for F3 model. Co-authors are Xuguang Wang and Yongming Wang. Using simple models, previous study hypothesized that hybridization of a static covariance with a flow-dependent ensemble-based covariance can take advantages of both. Using the real model, many studies have confirmed the benefits of hybrid covariance matrices for large-scale DA and NWP. The static covariance for large-scale DA has been established and widely used for long while. However, additional efforts are needed to construct a static covariance for convective scale DA and NWP. Wang and Wang 2021 has developed a convective scale static B for direct radar reflective simulation with the Wolf-ARW model, and found that the utilization of a convective scale static covariance matrix in the hybrid ENVAR can improve the convective scale analysis and prediction compared to using ensemble covariance alone. In our study, we further developed a convective scale static covariance for F3 LAM and examine its performance in RFS context. The new convective scale static B developed for F3 LAM is employed to directly simulate radar reflectivity using RFS 3D VAR and hybrid ENVAR frameworks. The following three questions will be addressed. Can we reduce the cost of convective scale static B without degrading much of its performance? What's the impact of using various hybridization or weighting between the ensemble-based and static covariances? How is the hybrid ENVAR compared to 3D VAR and the pure ENVAR? Emulating the RFS workflow, the DA and forecasting experiments are designed. Starting at 18 UTC, reflectivity is hourly assimilated from 19 UTC to 0 UTC. The 12-hour deterministic forecasts are launched at 21, 0, and 0 UTC. The selected case occurred on 26 and to 27 May 2021. It is featured with isolated and widely scattered supercells that grow upscale rapidly over the high plains. Based on the background ensemble generated through the co-stat forecasting from 5 cases using the F3 LAM, the static B is calculated by the ENS method with 180 ensemble members. Here shows the structure of the static B. For reflectivity, the large correlation coefficients are the consequence of rain falling freely under the 20th level. The variations of reflectivity at low levels are mostly affected by rainwater. Two maximum coefficients between relative humidity and reflectivity represent the source and the sink of precipitation respectively. In addition, the horizontal length scales for hydrometeors also physically reasonable. In practice, the first matrix on the right side of the echo is called physical transform. And the total number of physical transform coefficients is 66. To reduce the minimization cost, our approach is used to select and maintain the most critical cross-variable correlations. Taking the reflectivity as an example, we first calculate the ratio of explained variance to the total variance for reflectivity using 66 physical transform coefficients on the top. Then we only select and maintain the coefficients with the contribution larger than 10% to recalculate the explained variance ratio of reflectivity on the bottom. While the number of coefficients is reduced, we got a similar pattern of black dotted profile, which is the ratio of total explained variance relative to the total variance for reflectivity. After working on each control variables, 38 physical transform coefficients are selected, and we calculate the convective scale static B using relative dependent binning method. As a result, the minimization cost is reduced by about 25%. A pair of single cycle experiments are conducted using static B with 66 and 38 physical transform coefficients, respectively. We found slight differences in analysis and subsequent forecasts between two experiments. So we applied a new convective static B to 3D bar and hybrid in-var to explore the impact of hybridization. For hybrid, we added the static B to the entire domain with the weight of 30%. 19 UTC is the first cycle to assimilate reflectivity. 3D var and pure in-var start from the same first guess, but we can say they have different analyzed composite reflectivity. Through multiple cycles at 21 UTC, the trend of the analysis is consistent. Compared to the observation, 3D var, although 3D var has is much cheaper than pure in-var, it outperforms pure in-var in adding the mist storm in Kansas. By leveraging both the advantages of both 3D var and pure in-var, hybrid in-var performs better than pure in-var in adding the storm in Kansas and fits closer to the observation than 3D var. In terms of the subsequent forecasts, both 3D var and hybrid can capture the storm in Kansas, but pure in-var fails. Compared to the 3D var, hybrid better maintains the storm wind in the black circle during the later forecasts. For the analysis, at 0 UTC, 3D var still has an advantage to add the storm in the red circle compared to the pure in-var, but it has more spurious reflectivity, such as over the northern plains and the west of Kansas. Hybrid performs better than pure in-var in adding the storm in Kansas, but it can only partially addresses the spurious reflectivity compared to 3D var. We hypothesized that the spurious reflectivity in the vicinity of the main storms may be in hybrid may be attributed to the widely added static B. Therefore, the adaptive hybridization developed by Wang and Wang 2021 is introduced to improve the performance of hybridization. In adaptive hybridization, consider ratio is used as an indicator of ensemble quality to define the regions where the hybridization is required. In hybrid CR, the value of CR is set to 1.0. So the weight of static B is 30% when CR is less than 1.0. Otherwise, the static B is the weight of static B is 0. The right figure shows the diagnosed geographical mask based on the value of CR in the gray shadings outside the magenta contours. We add the static B from the being awake. In the green shadings inside the magenta contours, we add the static B from the being strong. Subjective and objective verification for the forecast initialized at 0 UTC are conducted to compare the performance between hybrid and hybrid CR. We can see that hybrid CR produce less spurious weak reflectivity than hybrid during the early forecast, and then hybrid better captures the reflectivity cost than hybrid. Objectively, the improved forecast skills in hybrid CR are well maintained throughout almost the whole forecast period. Finally, we are moving to the summary. The convective skill set B is further developed for every 3 lamp to directly assimilate reflectivity within the RFS hybrid UR system. To reduce the cost, an approach is used to select and maintain the most critical cross-variable correlations. Results on the impact of hybridization show that 3D bar with the new convective skill set B outperforms pure UR in adding the observed reflectivity. Hybrid UR can take advantages of 3D UR and pure UR. CR-based adaptive hybridization can further increase the forecast skills. Next step, we plan to conduct further research and development on adaptive weighting for convective skill DA. So I will stop here and take any questions. Thank you.
Thank you. I think, again, we're moving along quickly here, but need to move to the next presenter. Again, we're going to have time for questions after the break. So our next presenter is Tara Ladwig, and she's going to be talking about collaborative development on three-dimensional real-time mesoscale analysis.
All right, so yeah, we're expanding the short-range weather. I know a lot of the focus has been on the RFS, but the 3D RTMA is also a specific application of short-range weather, and that's the subject of this talk. This is collaborative development between GSL and EMC, and we've also have partners at SBC that have been helping us evaluate prototypes for 3D RTMA. So really quickly, we need a 3D RTMA instead of just a Rufus because we need timely analyses for situational awareness. We want these to be as accurate as possible, so very close fit to the observations. We also want these to be rapidly updating. So some of the existing 2D systems, they only leverage surface observations or are coarser resolution, more infrequent. Those types of things are inaccurate inadequate compared to what we're building for 3D RTMA. So there is an operational 2D RTMA, but our goal here is to transition to a 3D whole atmospheric analysis. Later, we're even longer term looking towards an on-demand, so continuous type analysis system. Currently, we're using 3D ENVAR for the data simulation, and the RTMA does support the National Digital Forecast Database, NDFD operations, as well as national centers, so our partners at SBC being example, as well as other user groups, aviation, fire weather, hydrology. So it's really a situational awareness tool and nowcasting tool. There is a companion system, the unrestricted mesoscale analysis. It runs in delayed real time, and it serves as NOAA's analysis of record. And this is really a key product for verification and calibration in the national blend of models. So definitely a lot of use by the National Weather Service for both the RTMA and the IRMA. All right, so the RTMA is the specific configuration of the Unified Forecast System, part of the short-range weather app that we've been talking about. And the RTMA really depends on the Rufus for background data. But there are some unique challenges to the 3D RTMA that go beyond the challenges we're facing for Rufus. One of those is just based on the sheer number of grid points. So We're going to be using this large North American domain for Rufus. That will apply to RTMA as well, but we also need a separate domain for Guam, and RTMA needs to provide products on these NDFD grids. So that's significantly more points. 2.5 kilometers, the NDFD grid for CONUS, Hawaii, and Guam. It's 1.25 for Puerto Rico, 3 kilometers for Alaska. So depending on all these different locations and the products that we need to serve to the National Weather Service that the current 2D RTMA is serving, we need to have even higher resolution in our final output. And that's definitely a challenge. So I wanted to note a few of the successes and a few of the challenges that we've been working with for 3D RTMA in UFS. RTMA is this specific configuration. It has its own configuration file and fix files. I'll note my colleague Ochinga has a poster about nesting data for Git repositories for some of these large fix files. We're able to really leverage the innovations in short-range weather, especially those from Rufus for RTMA. So it is definitely a companion system, and that's a huge benefit of working on the UFS system. One of the challenges is that we don't yet have any RTMA-specific testing in place. So upstream changes, whether those be from Rufus or on a larger scale in UFS and short-range weather, that requires our team to test them, to fix them, to get them going for RTMA. So we really need to have more testing in place and more specifics for upstream changes that we inherit so that that part goes a little bit more smoothly. RTMA, we did have support this year to run RTMA reliably in the cloud, which was pretty exciting. So that was support from OSTI, and we were able to provide data to the hazardous weather testbed with those runs. However, we did experience some challenges reporting to the cloud. It did require expert staff time. It did depend on data transfers from data on on-premises machines, our WCOS machines that were feeding the background data, feeding the observation data. So you have to wait for that. So the cloud runs couldn't be any faster because of those data transfers. There is also a poster from my colleague Raj Panda about cloud-based workflows for both Rufus and RTMA. So the RTMA schedule basically follows the Rufus schedule. So if we talked a little bit about the Rufus schedule changing and being pushed probably more towards FY25, so RTMA then subsequently follows that. So that window for RTMA is at least equal with or probably just after the Rufus window in 2025. We have been doing a lot of comparisons of our prototype RTMA systems. So these are comparisons showing 3D RTMA in blue, we'll say, and maybe greenish red for the 2D RTMA. But basically, the 3D RTMA is able to fit the surface observations more closely, and that's something that's really important to the users of the RTMA to have that close fit. Truth and accuracy of the observations is really important to the forecasters, and they really want that close fit for this analysis product. We've also been doing quite a few comparisons for the last several years at the HWT and working closely with our colleagues at SBC. So in 2021, the FE3-based RTMA was rated much worse or slightly worse compared to the HER-based RTMA. So this is an example of that, where these dots are kind of representing the fit to the observation. So you see a lot more larger size dots for the Rufus version in the center there compared to the HER-based version. But we did have a few aspects of the Rufus version that weren't implemented yet. And overall, the upscaled RTMA was rated just slightly worse than the SBC mesoanalysis. And that is another product that SBC uses that we're hoping to basically replace with this 3D RTMA. One of the other comparisons we did in 2021, it's really hard to be patient. Okay, we looked at the sub-hourly, so 15-minute RTMA data And this was subjectively, we got some good feedback on the usefulness of the sub-hourly data, and that's something that we'd like to provide with RTMA. I think the challenges associated with the large grid and number of points, we have to balance that with when we want to provide this on a 15-minute cadence compared to an hourly cadence. So that's under discussion of whether it will be a part of version 1 or a part of version 2. But being able to have that sub-hourly data can be really critical, especially for things like severe weather. In 2022 and 2023, the overall subjective ratings, and thanks again to our colleagues at SBC for providing this information. But the RTMA with FE3-based background was rated slightly worse to about the same. So those were the two most common ratings that were given. And in general, the analyses were similar, which is a good story. There were a few areas where we'd like to see improvements, and a lot of those were tied to the Rufus background. Oh my goodness. So this is one example where the thunderstorm outflows are really too cold, too expansive in the Rufus background, and that is then noticed significantly in the RTMA analysis. So what color is that? Green? Inside the circle there, you see a big displacement of color, and that's representing those colder temperatures that were in the Rufus background data that went into RTMA, and then in that RTMA analysis, then you see that bigger change, which is in this case over-representing what actually happened. We've also seen one of the other weaknesses, especially for this noted in this 2023 evaluation, was that the Rufus version was too moist in the dry air behind the dry line. So you can see that well in the difference plot on the right there compared to the HER-based version. So these are, again, things that we'd like the observations and the analysis part of the RTMA to correct, but we are, the analysis is working with that Rufus background. Okay, trying to pick up speed if it'll change. Okay, too far. We did have some exciting work in evaluating the analysis. So this is a screen capture from a website developed, again, this is supported by cloud funding and OSTI funding to help us basically evaluate the analysis and the data assimilation products. So looking at the fit to the observations, including spatial and temporal filtering. There was a lot of development to basically get the data processing to make this type of display possible. But I think the visualization system here is an important part of the data assimilation development so we can know how the data assimilation is performing. So just to summarize, if it does it, okay. RTMA does have this strong dependence on Rufus, both for technical developments and scientific innovations in the background data. For RTMA, the high resolution and low latency requirements are definitely challenging and are definitely unique aspects of this implementation of the short-range weather application. The observation quality control is definitely an essential area that we have ongoing development on, as well as uncertainty estimation. So there's a poster from my colleague related to work on uncertainties. And of course, we're looking forward to transitioning to JEDI for the RTMA data assimilation. I guess with that, we do have a job opening at GSL related to scientific programming for our RTMA project. If you want to spread the word, or that's definitely out there. Thank you.
Thank you, Tara. Thanks, Tara. We're going to have our next presenter, Malachi Pena from University of Connecticut. He's going to be talking about a consistent wind, wave, current analysis products with a 3D RTMA.
Okay, thank you. I want to present this collaborative project in which mostly oceanographers are trying to get involved into the development of the 3D RTMA. With the operational insertion of the significant wave height in 2017, a larger swath of users, specifically the coastal engineering, oceanographers, are paying attention to this type of new products. And so the intention of our project is to bridge this gap and to have some contribution specifically on their new developments in their own data simulation and the field campaigns that are carrying over specifically on the northeastern US. I'll explain in a minute. First, I want to thank my colleagues who were the main developers of this proposal. Stelios Enrique, who is in charge of the regional MOM6, Lionel, who is the expert on wave and current interactions, and Manuel Pondeca, who is our technical expert on the RTMA. Of course, I need to thank my colleagues at EMC and at GSL, Curtis and Isidora, and also collaborators of the JEDI project. So to go directly to the issue or the articulation of the goal is to advance data simulation of the surface wind, sea wave, and surface ocean currents. The philosophy of the RTMA, different from other types of data simulation schemes, is to be as close as possible to consistent observations. Rather than satisfying an best initial condition for a model, these are references that have to be solid in terms of consistent observations. So one of our main emphasis in this project is to improve or have more robust data quality control of especially new marine observations. I'll describe in a minute which is our focus right now, but we will start implementing more data platforms. So in parallel, we are developing this regional MOM6 at very high resolution, like 1/50, which is about 2 kilometers or between 2 kilometers and 1 kilometer. I don't know. How do I go forward? Yeah. So these are in red are the ones that we are currently developing, and in green are green color. Well, lighter color are those that we are expecting to develop in the next year. So the emphasis now, for now, is in the short term, is to work with the high-frequency radar data. We have collected data since 2006, and IOOS, NOAA IOOS has invested on this long-term network, and we would like to capitalize on that data set to create observations that could help us on nudging, for instance, the regional MOM6. These products currently are at 2 kilometers and 6 kilometer resolution. Unfortunately, we don't have an operational QC algorithm, at least not we are aware of. We have performing some validation, and we plan to utilize observing campaigns, the Pioneer Array, and some observations that are now available to get the more consistent evaluation of these fields. Here in this plot, we also overlay the JSON-3 satellite products of surface currents. These are derived by sea surface height. So as you can see, they are not easy to integrate with each other, despite that they measure or intend to measure surface currents. We can talk a little bit more about why they are not consistent with each other, but that's another topic. So we are utilizing also satellite altimetry data and comparing with surface winds. Specifically, we would like to see whether the type of biases and the information that they provide to analysis that are already developed. So here's a scatter plot. On the right shows, on the left, you see the general overpasses that happens within, let's say, 25 days. and we can see the large gaps that that they produce, but at the same time, how useful and consistent they are with the in situ observations. On the right, you see a scatter plot of buoys versus the different satellite missions. As I mentioned, one of the emphasis is to work with the experimental data and implement that into the IODA software and libraries to get two things. One is to have it as a quality control tool, and also to develop our forward operators. And another, and this is thanks to collaborations with SOFAR, they have a new network of buoy observations that provide wind vectors, wave vectors, significant wave height, and surface pressure. Sorry, there was a mistake here. And, but it has a good coverage, at least for the 3D RTMA that we are focusing on. Here is a loop of the 4-kilometer regional MOM6, which is a stable version. It consists of a time series of I think it's hourly outputs from 1993 to the present, and we are currently doing some developments of the most recent year at much higher resolution. The data is available publicly, so if others are interested, of course, they can access it. One of the main issues, or the core of this, or the research core of this project, is to understand the consistency of wind, waves, and currents. And some of our co-PIs have already developed some sensitivity studies on this type of situations in which, for instance, in this figure on top left, you see the surface, significant wave height and surface currents, and then without the currents, how much it impacts. Not only that, but the resolution of the currents plays a significant role in the description of the significant wave height. We are also doing diagnostics on the impact of the overpasses of altimetry data. This is an accumulated analysis increment and how it reduces errors the more overpasses we collect. And we plan to utilize this type of assessments for the developments of forward operators. We are also working on implementing a field alignment processing scheme. We got some experience with hurricane relocation, and we would like to apply it now to surface currents and significant wave height. So essentially, the scheme that we have is to subject the background field, the original background field, into a bias correction, field alignment bias correction, whenever the displacement errors are larger than a threshold that we tune in on our own. So we have several experiments, and we are testing new technologies on especially image registry to identify a best method, fast method to do this field alignment correction. Here is a comparison of experimental 3D RTMA versus the RTMA wind speed. We are interested on the coastal and the open ocean, and here is one of the results that we just plot for you to visualize the issues that we have, especially near the coast. So let me see. Yeah, so on top is a buoy that is between about 100 kilometers from the coast, and then when the station is like more than 100 kilometers, and as you can see, the problems that we have near the coast, not even coastal, it's just near coast, and we see buoy in, well, it's difficult to differentiate, but it's all over the place. So one of the main reasons that we have for the improvements on data assimilation of wind is the lack of observation. So we expect to enhance this, hopefully, with the high-frequency radar and other measurements that are already available. Finally, the other aspect that we are concerned is about the systematic errors. So we compiled 5 years of the latest HER at 1 hour forecast, and then compare that with LiDAR data, one LiDAR data that we work with in the New England region. We noticed that there is like 30 minutes lag, and then we developed some technologies or some techniques to do time warping systematic errors to allow this nonlinear bias in time. In connection with the industry, which is also co-funding some of the observations that we are using in this project, is they are mostly interested on wind ramps rather than the time series itself. And so they are interested on understanding whether our models are capable of predicting big jumps in the wind. So in these bivariate histograms, we can see ramps on the vertical, and these are the duration of the ramps on the horizontal, and the panel on the left is the LiDAR data, then the raw HER, and then as you can see, the impact of fast ramps, which happens in the first column. So you see they are missing. That means we missed a lot of this rapid increase in amplitude during the first 1 hour or 2 hours. This is data compiled every 15 minutes. And we can see that even when we do the typical amplitude bias correction, we don't actually increase the bivariate distribution, but when we do phase alignment, we get this nice description. So to close, to wrap up, now is trying to, yeah. So what's coming up in the next few months is we continue working with porting the UFS framework of the regional MOM6 into our computers, and then work with the workflow management to integrate this new software. With Stelios, we are working on improving the background error covariance of wind waves and continue developing metrics for the consistency of the 3 fields. And that's all. Thanks.
Thank you. So I think we're on to our last presenter before the break. Adam Clark's going to be talking about evaluations of 3 MPAS configurations in the spring forecast experiment from NSSL. So take it away, Adam. Thank you.
There's first, lots of great people from different agencies contributing here. So NCAR, GSL, SPC, and CRO. All right, so our spring forecasting experiments, these are co-led by the Storm Prediction Center and the National Severe Storms Laboratory. Our 23 experiment was hybrid. It was the first time that we had in-person folks since before COVID in 2019. So we had 50 remote participants and 77 in person. Our main goals really were trying to improve severe weather prediction. So we're evaluating emerging technologies, accelerating research to operations. And one of the really important things, especially in the context of this meeting, is that we're facilitating experiments to evaluate and try to optimize deterministic and ensemble CAMs to inform the UFS. And we use this framework that we call the Community Leverage Unified Ensemble. Essentially, this is just a way to coordinate all the different model contributions that we have from our collaborators. So one of the cool things that we did this year, and I'm also noticing this isn't my updated slide deck, that's okay. I will go with this one. We evaluated 3 configurations of MPAS that were run regionally over the CONUS. So let me move on to this one. This is just a table showing all of the different contributions to the clue. So we had EMC and GSL contributing, NSSL, GFDL, NASA, and then NCAR. So what I have highlighted here in red, those are 3 configurations of MPAS that we evaluated. I also wanted to note that NCAR contributed 5 members of MPAS initialized from GEFS members that we evaluated. I won't be looking at that here, but talk to me if you're interested in those results. So we have a real-time web viewer where you can go look at these forecasts. They're not just limited to the spring forecasting experiment. We're doing these year-round. So check out cams.nssl.noaa.gov. You can look at those in real time. So, all right, just a brief look at all of the different model evaluation activities that we did in the SFE this year. I wanted to highlight the things that have the red boxes. Those are all MPAS related evaluations. The one that I'm going to be focused on in this presentation is D5, and those are the 3 configurations that NSSL ran. Okay, so to start looking at some of these results, this is just an example of the deterministic comparisons that we do. It's what the model comparison webpage looks like when we do these subjective evaluations. So we're examining updraft helicity and composite reflectivity for the 12 to 36 hour forecast period, and the things we're really focusing on are the timing of convective initiation, the mode of convection, displacement errors, that type of thing. Importantly, these comparisons were blinded. So you see the labels on these panels, those were not there when we did these evaluations. So we're trying to get rid of any explicit or implicit biases from the participants. Okay, so Israel showed these, so I won't dwell on this too much. This is just a summary of our subjective ratings for the 5 different deterministic flagship comparisons that we do. And what I wanted to highlight, well, first of all, HERV4 was the clear top performer, but the MPAS run that was initialized from the RRFS and used the Thomson microphysics was a close runner-up, and it actually performed quite a bit better than the RRFS from which it was initialized. So what's interesting to me is that the results from 2022 were a little bit different. So RRFS performed more favorably compared to HERV4. So what happened? I have just a couple hypotheses that I think make sense. RRFS implemented the radar DA in 2023, and we see this very clear problem with the intensity bias and then the spurious convection near the time of initialization. And when we tried to implement FV3 in WAFs, we saw the same thing. Also, it was a relatively quiet weather regime, lots of weakly forced events. You know, something that Lou talked about is that those biases in FV3 seem to be a lot more apparent in these types of regimes. Okay, so just an example of kind of how we do these. I think it's important to show, you know, what we actually look at when we do the evaluations. So this is just showing just kind of a random case where at the beginning of the forecast you had a dissipating MCS over North Texas. Oh, this is going to like take forever. It's like an animation, but I have to click forward each time. So let's see if how long it takes. Okay, so you have a dissipating MCS. All the determinists, oh boy, there it goes. Okay, so the point here is that if you look at the bottom right in the observations, there's this kind of disorganized linear system over West Texas. If you look at the HER, which is in the bottom middle, it depicts this pretty well. But if you look at the top middle and the top right, you have the RRFS, and then you have the MPAS that was initialized from the RRFS. They have spurious convection in central Texas. And that wipes away some of the instability so that when that convection in West Texas moves to the east, it's not going to have the instability that it needs to maintain itself, and you'll see that has an impact on the evolution of the system. So these are kind of, the types of things that we look for when we do this. Okay, this is killing me. All right, hey, there we go. And it's going. Okay. So there's everything that I talked about here. Oh my gosh. Okay, is it just going to keep going? All right. So we also looked at the environment fields in these different deterministic models, and it's just going on its own now, so I probably pressed the arrow button too many times. But for the environment fields, there were kind of mixed results depending on what field that you looked at. But if you look at things in the aggregate, which I do have on a slide. Okay, I'm being real careful now. Okay, so these are the aggregate results for the environment fields. And you see her as the clear winner, you can call it. But the MPAS run initialized from RRFS performs a little bit better than the RRFS itself. So this is separate from the reflectivity in the UH comparison. So MPAS is also performing favorably for the environment fields. Okay, so now I've mainly looked at the RRFS initialized MPAS. Now I'm going to look at the two versions that were initialized from the HER. So we did this 4-panel comparison where you have each of those 3 MPAS configs, and then you have the OBS in the bottom right. Okay, so what we found is that of the 3 configurations, it was actually the one initialized from HER that used the NISL microphysics that performed the best. So why did it perform the best? Wow. So the point I was going to make before I talk about the why is that if we would have put that MPAS HN up against the other deterministic models, we probably would have seen a more favorable result, since the RT run there was the relative worst performer out of all the MPAS runs. Okay, now to the why. All right, so this was just a case where you had a line of storms going through southern Missouri, and the observations in the bottom right, you can see that in the HT and the RT runs, it's much more expansive than it is in the observations. In the HN run, so the HER NISL microphysics run, captures that evolution more closely to the observations. So, excuse me, some of the participant comments are shown on the left. A lot of folks mention things about placement, the mode, the evolution, the organization, the structure, that sort of thing, tended to look better in those NISL microphysics runs. Okay, so what's going on? It's really clear that the MPAS RT runs are inheriting errors in the RRFS initial conditions. So I'm showing a 1-hour forecast. On the left is RRFS, the middle is the HER, right is the OBS. You see this clear intensity bias in the RRFS, and then I'm going to show the MPAS runs initialized from those 2 data sets, and it's very obvious if they will pop up. Okay. There, that they're inheriting those errors. So I think that explains some of the things that we're seeing. Oh, this just keeps going. When we looked at the really short-term forecasts, we saw this very clearly. So the HER ended up being rated higher for both 1-hour and 6-hour forecasts compared to RRFS because of these intensity biases. So people commented on this quite a bit. Our RFS was too hot, reflectivity bias, misleads with spurious convection, things like that. Okay, so I'll wrap it up. These MPAS configurations performed quite well. I think it's notable that the RT outperformed the RRFS from which it was initialized, and we have these major issues with intensity biases. For the extended range prediction, I did want to note that the 5-member MPAS, when we compared it to the 5-member FV3, for all lead times performed significantly better. So what's next? We're going to implement MPAS with WAFs, and we think we've made a lot of progress in a short period of time. So big credit to developers at NCAR and also NOAA management and everybody supporting this work. So thank you.
All right, thank you, Adam. And I want to thank all 7 of our presenters again from this morning's session. So thank you all. Break now, and we're going to be back in here right at 11. And then I'm going to have a brief presentation that'll segue us into discussion and Q&A for the better part of an hour. So hopefully we'll see many people back here in about 22 minutes. Thanks, everybody.
I'm not sure if everyone in the hallway knew we were getting started, but we'll go ahead and get started. We have an hour session here on the short range weather. We're going to start with a presentation from Curtis Alexander, and then we'll have questions and discussion from all of our morning session here. So take it away, Curtis.
All right, thank you, Tara. Yeah, thanks again for, I guess, an opportunity to talk a bit about where we're going with the rapid refresh forecast system. Now that we've resolved our plans for the first operational version, we're going to talk about what's beyond that. The number of modeling systems in the production suite is certainly well established now as a mission of the UFS. I think we're certainly on the way to that production suite simplification. I don't need to spend much more time on motivating that here. Again, we've got this brand new big 3-kilometer RFS domain that's going to be much larger than any individual CAM domain that we have currently in operations. That's going to help consolidate those modeling systems. The plan is to not change this big domain for the second version of RFS, so we've established what it looks like for the first version, and so the scope of the domain itself, we're not envisioning currently to be something we want to iterate on for a second version. I do want to emphasize the tremendous amount of development effort that's taken place with V1, building a regional-only version of FE3, getting a CCPP interface established to work with the physics suite, all of these physics, data assimilation, and then testing and evaluation capabilities, let alone all of the UFS short-range weather app releases that have gone out over the last several years. So there's just a tremendous amount of work that has gone on really over the last 5 years leading up to this maturity or the maturing of RFS V1. I just want to highlight a seasonal bias reduction that we can highlight as an example of the work that's been done. These are 2-meter temperature and dew point by season from top to bottom. Forecast length is the y-axis, valid time x-axis. The point is the HRR has an operational known warm dry bias you see at the bottom during the summer, during the daytime. We've gotten to a point with the RFS where we've ameliorated those types of biases, and that's the type of thing we want to carry forward, not only in V1, but beyond that. We've already talked about what the V1 deterministic and ensemble forecast cadence is probably going to look like. One nuance here is we're revisiting more ensemble members concurrently with a shorter forecast horizon as the trade-off for that, the 48 rather than 60 hours. That said, for V2, we're certainly going to look at other combinations of cycles and membership for more frequent ensemble forecast guidance, because that's something we definitely need to move toward for forecast applications, convection allowing prediction in general. So that's an area of emphasis we're going to have for V2. In terms of physics, this is the physics suite as it looks for V1. There's already been a lot of discussion about this and where we're at, and this is based largely off our experiences with the RAP-HRR physics development over the years. For V2, we are planning to switch to the NOAA-MP land surface model as part of the unification of physics suite across scales. There's some details we need to work on and how that'll play out in terms of bringing in regional capabilities in terms of land surface model treatment with observations and data assimilation. Won't spend any more time on that now, but I just want to make that a point of emphasis for physics going into V2. We'll also be looking at RRTMGP for the radiation scheme in V2 as well. So those are two parameterizations that we're anticipating evolving as we move into the second version. Data assimilation highlights. Another big one is we've got to get to JEDI. So the plan is to move all of the DA infrastructure analysis capabilities, everything into the JEDI framework for V2. So we'll be finally putting a GSI to bed at the end of V1. We're going to get from what we call a moderately coupled soil DA adjustment to a strongly coupled approach where we're using soil moisture temperature observations and covariance information across the Earth system components with an ensemble to help do the truly strongly coupled land atmosphere DA. So we'll be leveraging building off of what we've been doing with the RAP-HRR and RFS V1 where we just update the soil state based on the atmospheric analysis increments only. In terms of cycling, we have this partial cycling approach for V1 where we're going to inject large-scale information periodically into the regional CAM analysis system. We'll be doing this roughly 2 times per day. Again, this is something we've done in the past with the RAP. That does have complexity and more cost to it by doing this partial cycle spin-up. I think for V2, we're looking at a more sophisticated and computationally more efficient and simplified approach of blending in information across wavelengths from the global information into the regional hourly cycled system. We may have some components of this in V1, but I think a truly blended solution each hour where we don't have to have a partial cycle is definitely a vision for V2. Another aspect of V2 data assimilation is going to be including the better strategies for handling highly latent observations. Satellite data comes to mind in particular. Overlapping windows is a technique that's been developed and tested with PSL, EMC, GSL collaborative developments, and I think that technique can be leveraged in the future, again, without having to do partial cycling to bring in latent observations into the hourly cycled system. So I think that's definitely another thing to look forward to in V2. Other observation types we may bring in include synthetic satellite radar that's basically a neural net retrieval of GOES channel information to produce a synthetic radar product that we can leverage outside of conventional radar coverage. The Rufus has a very large oceanic domain outside of conventional radar coverage, so we value work and collaboration like this that I think is going to help us long-term in terms of improving forecast prediction, again, particularly in areas outside of other conventional radar coverage. Another aspect of the DA improvements, we have this sort of poor man's multi-scale DA sequencing going on with V1 that harks back again to the RAP-HER systems where we run the analysis system multiple times with different observation types, different length scales, and then finally the hydrometeor analysis at the full native model grid resolution. And so we want to really move to a multi-scale DA approach where we can consolidate all of these steps into a singular analysis approach. That's going to be more efficient and ultimately scientifically more effective to combine all of these, like I said, into a singular analysis cycle. One thing we have noted, and I think this was touched upon in other presentations in the session before the break, bringing in radar data, reflectivity data into the RFS has improved its skill, but it's also raising its bias. And so we think we saw the imprint of that this spring in the forecast experiment evaluations at the test bed, where the early forecast hours coming out of the RFS, particularly in the evening where the convective cycle is most active, showed an increase in bias in the first few hours significantly, particularly at higher thresholds. And that's shown here in a controlled experiment of running and rerunning the configuration with and without radar reflectivity data. So rest assured the red line is the highest one on the bias plot, and that's the one with the radar data. So just to give you an idea of this challenge that we're having in terms of cycle data simulation with the model's response to that. Dynamic core, this has also been touched on this morning. We are seeing this high bias of high precipitation at the higher thresholds. What I've done here is just looked at this spring's precipitation forecast biases. Operational HER at left, the Rufus that was evaluated at right, spring and now summer in the upper and lower rows, and stratified by 1, 6, and 12-hour forecast lengths, which you won't be able to tell. However, that doesn't really matter in the broad context here. The reality is, as you look at the Rufus forecasts at higher thresholds, 1 to 3 inches in a 1 to 12-hour period, the curves go very high very quickly in terms of bias. So we're still seeing that high bias for higher precipitation forecasts. The HER has its own biases. It is certainly not perfect. It has a low bias at low thresholds. But again, our biggest concern right now is this high bias at higher thresholds. So as Adam mentioned, we also, NSSL ran several MPAS configurations this spring that were fed from HER or Rufus initial conditions. And these are radar reflectivity verification from 15 to 45 dBz, again, all focusing on bias at different forecast lengths. You'll notice that the 1 hour forecast, that highest curve on there is the RFS, so it's going up to a 4 or 5 bias, frequency bias at 45 dBz, and it would be higher if we traced out to 50 or beyond dBz. That comes down at the longer forecast lengths as you move away from the analysis and the influences of the data assimilation. but it's still one of the higher forecasted bias curves, particularly again as you get to the high thresholds. At the lower thresholds, it actually becomes pretty optimal. I better not move. Wow. Okay. I wish I had that power for other things. So now that we can see color, basically the point here is that we see a high bias with the FE3 based RFS, particularly at short forecast lengths coming out of the data simulation, but also persistent at high thresholds across these various forecast lengths. One thing you'll notice at the lower right, again, the RFS bias for lower reflectivity thresholds is pretty optimal, but even at the high thresholds at long forecast lengths, it is rapidly increasing, and the Rufus initial condition initialized MPAS run actually has a pretty level bias at those high thresholds using those same initial conditions that were produced from the RFS itself. So I think that can be pretty telling in terms of an impact on just switching the die core and keeping pretty much everything else the same. The last thing I'll highlight here is sort of the merger of some of the subjective and objective evaluation in terms of storm structure. This is one of those spring forecast experiment evaluations, one case day, the 31st of May, operational HER, along with the Rufus A, and then the MPAS initialized from Rufus A forecast, and you see that characteristic Rufus A convective structure at upper right where all of the convection looks relatively circular and very intense. There's not much discrimination in terms of intensity as opposed to the HER, which granted is missing some of the convective evolution in Kansas, where MPAS I think is inheriting some of the benefits of the Rufus data assimilation, is getting some of that convective development in Kansas, but doesn't have that everything is, you know, an extremely intense, severe cell. There's more dynamic range to the size and intensity. And NSSL has done some object-oriented verification both last spring and this spring from the spring forecast experiment data, both looking at the Rufus forecasts, HER, and then truth with MRMS, identifying objects by type, whether they are ordinary, supercell, QLCS, clusters, etc. And they provided this analysis comparing the distribution of these convective objects from the HER to the Rufus against truth, in this case, again, the MRMS radar reflectivity data, large sample size data set. And you can see the distribution of structures classified by this approach by different cell types. And again, the big picture theme here is, and these are basically density functions across reflectivity threshold for composite reflectivity, that there's a tendency for the RFS to be on the high end for reflectivity and frequency of these certain types of convective structures. Again, the supercells and QLCS, or should say ordinary cells, compared to both the HER and the truth RFS. And you can combine those four into this composite at left to show that the RFS actually moves a bit further away from the truth in terms of the storm type differences. This spring, they also added an analysis for storm structure looking at solidity, sort of measured by the area of the convective feature compared to a convex hull. So this is a value that ranges from 0 to 1 effectively. As you approach 1, you're getting to this more concentrated circular shape where the area and the convex hull basically approach the same value. So from data sets looked at just this spring in the forecast experiment, again, you're seeing this separation of storm structure from MPAS initialized forecasts or HER forecasts compared to the truth and MRMS, which is in black, being quite a bit less frequent in terms of solidity, or lower, less solidity, I should say, less circular, if you want to think about it that way, than the RFS forecast. So this quantifies what I just showed qualitatively in that example earlier from that event case in Kansas. Okay, so status summary. Again, we're looking at an RFS major upgrade that has a lot of benefits compared to the existing CAM systems. We're going to be providing CAM coverage over a bigger domain, longer forecast lengths, a coordinated ensemble forecast with the deterministic forecast. We are scheduling an implementation for this in FY25 with a code freeze somewhere between this fall and next spring. Obviously, there's a lot of benefits that we want to bring into this in terms of the advanced scale-aware physics, the improved data assimilation, direct radar reflectivity, et cetera. And so this is certainly where we're sitting with V1, but we do have these convective scale structure and bias challenges. And then I've highlighted, I'm not going to go back through them here, a lot of the potential that exists for RFS v2 and beyond that include domain expansion, JEDI transition, more observations we want to assimilate, physics transition, no LSM, et cetera. And the last bullet point I'll mention there is, given the observations, the experiments, and the sort of experience to date that we're having with MPAS, I think we ask ourselves the question, and we need to explore a transition to MPAS as the dynamic core for V2. So I'll reiterate some of the findings. Again, Lou, I think, highlighted a lot of this nicely in his presentation on the FE3 design for vorticity dynamics being good at large scales, but we've got challenges here at CAM application scale for representing convection and the tendency to produce spurious storms, which I think gets exacerbated by our data assimilation, that as we cycle more frequently with that high model bias, we continue to excite and trigger more excessive convection in a runaway state. So this is a big challenge for a lot of these different applications like one-on forecast, as they've mentioned. The moving vertical coordinate can also be a challenge for these convective scale applications. Obviously, there's a tendency for these surfaces to potentially collapse, becoming numerically unstable, even with small time stepping in the presence of strong convective updrafts. And then the physics tendencies currently, and this has been well documented, I think, by EMC as well, Kevin Viner, are implemented in a way that's not traditionally used with other models, and how the physics tendencies are applied during the dynamics time stepping. So this could be addressed, but certainly not in a trivial way. So finally, I know people are going to ask this question, why not just jump to V2? Well, we're already T+6 or 4 or 2 years away from the last CAM implementation for any of the legacy systems. We're also facing another computer moratorium coming up in FY26. So the time is of the essence to, I would say, solidify the state of RFS v1 to a point that's acceptable to stakeholders. And so if we want to accomplish any sort of CAM upgrade before FY27, this is something we really need to come up with a satisfactory resolution, like I said, this fall into the winter time, lest we're going to be running up against that next scheduling constraint. There's a lot of things that would have to happen for us to do an MPAS transition for Rufus. We don't want to do a GSI MPAS route. There's a lot of work with GSI that would be needed to deal with an unstructured grid directly interfacing with it. So I think investing more time into GSI development is going to pull us further away from where we need to go data assimilation-wise and moving to JEDI. But time is going to be needed to get a true JEDI MPAS solution in place. And then the physics, we don't have all the physics capabilities in MPAS we need right now. Stochastic physics being one of them for part of the RFS ensemble. So there's more work that needs to happen there on the MPAS front. So there's just a lot of things that have to happen to get us to an MPAS type solution. Given all of this, like I said, I think the best case scenario for a V2 implementation is probably FY27. But V1 has a lot of benefits, a lot of bias reduction that I've already talked about in terms of the mesoscale environment, and other benefits here that we really need to bring over the threshold in the shorter term. So that is the challenge. But like I said, I think we are going to be looking at MPAS as a possibility for RFS V2. So I will end there and pivot to questions, answers, discussion for the next 40-some minutes. So.
Thanks, Curtis. I think we had a few online questions that were from our earlier talks today. I think there are several related to the discussion of the dynamical core. So Aaron, I believe, was going to read those questions. Thanks, Aaron. Maybe we'll start with ones that aren't the dynamical core to get those in first.
Okay, can you hear me? Okay. All right, first question I have is from Joseph, and I apologize for the pronunciation of the last name. I think it's Moalim. And the question is, can you elaborate on the configuration of the FE3 Solo model? We have a flexible Solo framework where setup parameters are configured differently for each case.
Yeah.
I'm back. There it is. Real quick, FE3 Solo has been a nice tool to use, and I have tried to configure it with RRFS type parameters, the same with WRF and CM1. I've used the damping, the evection schemes, all those types of things. The Kessler microphysics. I've also implemented the linearization of the vertical semi-implicit solver to make W and DZDT match better. The only thing I'm not doing like RRFS, and that includes for the CM1 and WRF, is I'm not running a Rayleigh damper in the stratosphere because I was sort of messing around looking at that W DZDT inconsistency later, and I just never turned it back on. So I think it's actually, unless there's something that I'm really missing and don't understand, I think it's configured relatively similar to the other models. I've tried to match the vertical dissipation by removing it and things like that. So it's very hard to do. It's very hard to set up these very different models exactly the same, but I've tried to do it. So I'll be glad to talk to you more about this offline, Joseph, if you'd like to send me an email.
Thanks, Lou. Okay, Aaron, go ahead with the other questions.
Okay, let's see. Second question, really more of a comment and question from our Clifford Bass. Says we have a serious problem. The FE3 core is essentially flawed at convective scales. The one on forecast folks rejected FE3. What are we going to do? Replace with impasse.
Yeah, so I don't know if Curtis, you'd like to start that since you've addressed some of that with these plans for or potential ideas for Rufus version 2.
Yeah, I guess, as just reiterating what I put up here on the slides, I think we have identified a serious issue with FE3 for convective allowing model applications that are, of interest to stakeholders like the Storm Prediction Center and others. And I think it does necessitate looking at another dynamic core. MPAS is, I think, our obvious candidate to do that. That said, we also really need to get these innovations that have been developed and matured over the last couple of years for V1 of RFS into operations. So, and I think Matt alluded to this earlier, there are a few physics or physically based issue or approaches that we're looking at right now, like convective parameterization at 3 kilometers, perhaps revisiting the physics dynamics coupling, that are things that may help ameliorate the biases enough to make it acceptable for V1 implementation with FE3. There are multiple aspects of that bias characteristic. There's storm structure, there's coverage, there's intensity. I think the physics or physically based approaches that we're exploring right now may help reduce one or two of those three, but I think there's still some fundamental dynamics in play that we're not going to be able to ameliorate all of that. But will it be enough for stakeholders? And we really, again, given this timetable we're up against, really would be beneficial to get the V1 into operations and bring a lot of benefit, let alone simplification of the production suite and consolidation of resources, staffing-wise, compute-wise, et cetera, to the table. So I'll leave it at that.
Thanks, Curtis. We have additional comments from Lou here on that question. Yes. And then also just want to note, those of you in the room, you're welcome to stand up when you'd like to ask a question or make a comment. You can use the mic in the back with Aaron or the mic up here. Just stand up and we'll get you on.
So I just want to make it, I'm not speaking for EMC. I'm not even sure I'm speaking for NSSL. I'm speaking for myself. I don't think we have to look at this problem. I mean, it's a thorny problem as a 0-1 answer. I think we have to look at it. We have a lot of smart people in our community, and I think we have a way of trying to maximize the best benefit out of any systems that we have and go forward here. So I don't think it's just a choice between scrapping this or living with this or waiting 5 years. I think there are ways that we can work together to mitigate risk and create a scenario where we can evolve our systems in a rational way rather than going on this sort of massive program, which has been sort of way, frankly, since I've been in NOAA, seeing things happen at times. So I would encourage people to think outside the box about how we can really make this work in a way that we try to maximize what we've done and you take advantage of that, and yet preserve the forecast quality, and then move forward from there. Thank you.
Thanks, Lou. Other comments on this one in the room? Quiet group at the moment. Okay, Aaron, I guess go ahead with the next online comment.
This next question is for the first speaker. I believe that was Matt Powell. Why is the long-term plan for RRFS still single physics if multi-physics gives better ensemble characteristics?
Well, I sort of responded in the Slido that I don't think it's unambiguously better with the multi-physics, but the reason why single physics is sort of the desired outcome is just for better simplification and better code management going forward, not to have to maintain multiple physics suites.
Thanks.
One comment, I think it also depends on what are the metrics you're looking at for ensemble performance. I think the single physics approach gives ensemble attributes you cannot reproduce with a multi-physics approach. And so I think you have to understand that if you really want an ensemble of equal likelihood of all members, for example, and looking at the density of solutions, that's not something you can do with a mixed physics ensemble where you have disparate biases. So it's not, and so I think there's information content in changing the ensemble design that is as of yet unrealized, since we haven't had a CAM ensemble designed like that. So I'll leave it at that.
Knock, knock. Okay. Just a quick thought on, I think the RFS V1, in terms of getting it in front of stakeholders, I think that process is a really important one in terms of weather service priorities. You know, our priority to me is absolutely we got to get rid of some of these legacy systems. I think the ensemble approach to and incorporating that into the evaluation process so that we can, so we're not just evaluating the V1, RFS V1 as a deterministic system. Because if we do that, I don't think it's going to pass the muster when it comes to SPC evaluation, WPC evaluation. And so I think it's important to know that everybody's kind of on the same page in terms of understanding the process that we have to go through in order to get our RFS V1 into operations. Brian, I know you can speak to that pretty clearly, but I think it's important that everybody kind of knows what that process is and is reminded of what that process is. Some of us know, some of us don't probably. But also, I think getting to Lou's point, we really got to think about, you know, thinking outside the box in terms of how to message this RFS V1 implementation, but include, to me, the ensemble approach, which is where we're all going anyway. And I would also say, you know, potentially WAFs too. It could be part of that, maybe not part of the evaluation process, but it is a system that will help the forecaster if there are certain challenges that they have with RFS V1. So, Brian, I don't know if you want to address that or not.
So yeah, for those of you that don't know, the implementation process in the Weather Service to actually get something into operations from code freeze to turning on WCOS is about 1.5 years, maybe a little shorter. So the code freeze, when all of these things need to be fleshed out, is going to come a long time before it's actually implemented operationally. So Lou, I want to put a little bit of a caveat onto your statement. There are schedule constraints in the operational system that we need to recognize. One of them is an upcoming moratorium, which means no new implementations for about 1 year, currently scheduled for February of 2026. And the good news is we're doing a moratorium because WCOS is going to get upgraded. Don't know what that's going to look like quite yet, but we know that that's a hard fix. So if you do the math, right, the last code freeze that we can do is going to be somewhere in the fall of 20, God, can I do the math? That's a good question. Basically next fall, right? On top of that, RFS is not the only system we're looking to upgrade, right? The global systems next door is just as big, if not bigger beast than the RFS. And we certainly can't do all of those things at once. So we do have to stagger the implementations accordingly. So these are the kinds of constraints that drive us toward having to make, it's not a continuum of decisions. Maybe it's not a 0 or a 1, but it's getting pretty close based on these kinds of constraints. Right. Mm-hmm. Yeah. So for those that didn't hear Lou, which I would find surprising, but anyway, Lou made a good point, right? Some of this stuff is not set in stone, and I think for my part, we need to be as agile as possible in adapting to any of these kinds of changes. There was one more thing that I was going to mention, and I can't remember what it was. So that's all right. It's all right. All right. If I think of it, I'll come back.
Thank you, Brian. We'll go to a question in the room, and then we'll go back to online questions.
Yeah, I think there's lots of interesting aspects here in science, forecasting, and perception, but I just wanted to also talk about an infrastructure aspect. So when we talk about MPAS, sometimes we're talking about MPAS DICOR, and sometimes we're talking about MPAS entire model. And I think as we go forward with this discussion, it's really important to involve the groups working in infrastructure. I'm looking at Arun back there, and think if we are going to be, dropping MPAS, DICOR into the UFS structure or using MPAS, standalone. Those types of solutions take time to accomplish. There was a comment here, put CCPP framework into MPAS. That sounds like a standalone MPAS solution. If we bring MPAS into UFS Dynamical Core, CCPP is already there. So I don't want to get into the weeds or get an answer. I just want to say there are very important discussions to happen on the infrastructure side, and let's get those going so we can get the answers in due time.
Great point, Leisha. I see you remembered.
Sometimes it just takes a little while for the little people in your head to walk across from the left hemisphere to the right hemisphere. So the one thing I wanted to mention has to do with what Danae brought up, and that is the sunsetting of legacy systems. One of the reasons that we're doing the UFS is to simplify the production suite, to have fewer systems that we have to develop and implement. For those of you that are aware of the HAFS implementation late last month, that came with the proviso that we would continue running a few members of HWRF and HMON alongside of HAFS, right? That was not in the original plan, but our customers, primarily the National Hurricane Center, wanted that level of comparison available to them during this hurricane season. The plan is to get rid of HWRF and HMON at the end of this hurricane season and just go forward with HAFS. If you look at that same thing for the mesoscale systems with the moratorium and the work that it would take to transfer not just RFS to a new architecture potentially, but all of the current legacy systems, if we do not implement RFS and sunset those legacy systems, it is an enormous amount of work. And frankly, it's a big concern, even if RFS were implemented operationally, if we don't sunset those legacy applications, that's a workload that we're going to have to figure out how to accommodate, right? Huge load on EMC. I'm being a little parochial here, but it's a huge load on EMC, right? Big driver for us wanting to sunset the legacy systems, and we're not there right now.
Thank you. All right, so we'll take the next online comment, Aaron.
Okay, so I've got a couple of questions here. First is it possible or does it make sense to use C-grid with the FV3 core instead of D-grid to alleviate the damping issue?
No. YJ, I tried to answer this. I'll just be really brief. I think that's a possibility. I think the question we have is this modeling system what we think we're going to be running in 2035? And I think we are going to have to go through a substantial development cycle for GPU. I think we're going to need partners for that in order to increase efficiency and electricity usage. So I think that, and then there are other societal and community issues that I think go on with that. So I think if you look at the cost benefit, in my opinion, which I'm certainly probably biased, I think the answer is it's not probably worthwhile. And I'm not sure the model developers at GFDL agree that there's a significant problem here. So then again, who's going to do all that?
Oh, yeah, another comment? You can use that one.
Is this working? Another comment I would bring up is that I don't think the convection allowing issues are the only ones with the die core. I think we've run into plenty of other stability issues, such that switching C-grid would not alleviate everything anyway, and there would be a lot of work left to do. So, yeah, I don't really see that as a viable option.
Thank you. All right, we'll take the next one from online, Aaron.
Okay, and this next is more of a comment from Lucas Harris. Said the NSSO presentation was extremely questionable. I would like to address it verbally. Also, nobody has answered Joseph's question.
Does that mean, can we hear people online? I don't know if that's possible.
Yeah, I mean, there's some replies here. If you want me to kind of go through those, I can. Okay.
Lucas is actually saying post that or not, but
I do see where Lucas did say thanks because the question was answered earlier. So.
I'm sorry, could you speak up a little bit? You have a very soft voice, which is.
Okay, so how's that? Is that better?
Yeah.
Okay. But yeah, Lucas was saying Joseph's question, well, it said in the comments that Joseph's question was answered earlier, so Lucas was just saying thanks for that.
Oh,
so,
okay, great.
Yeah.
Great. Was that the end of the online questions, or did we have? Yeah.
Yes, for now.
Okay, great. We have one in the room. We can.
So just a little comment about sort of the bigger picture of how we sort of envision in UFS and operations, and the fact that those are two different things. So if you talk about what Brian was talking about a little earlier, all these arguments are not science arguments, they are operational and engineering arguments. And so that is one side of the equation. And so the UFS, as has been developed and mature, is getting mature for the operational side. In the meantime, if you look at how we use this same thing for instance, the wave model or for the ice model, how we do development there is nothing wrong with. Actually, it's very healthy to have additional options available to do research with. And so if we are saying we need to do more research with the MPAS, it doesn't mean that we have to make it ready for Brian before we can do anything. It means that if the people who want to work with that code, either in the UFS or outside the UFS, see value of putting it in the UFS so they can do easier comparisons, easier development themselves, can compare apples to apples because they're all in the same framework. All these arguments are good arguments for somebody to bring in an MPAS die core into a UFS. Just don't let Brian pay for it. Don't try and make this completely ready for operations yet. Bring it into the framework with research funding from inside of NOAA or from outside of NOAA, and we'll see where the evidence brings us whether we need two die cores or not. And by the way, it's the unified system, it's not the unitary system. And this is the same thing I said in response to Lou's talk last week. Just look at what we're doing. On the ocean side in the UFS, we need a separate numerical solution for the deep ocean, for water quality and navigation on the coast, and for storm surges. We don't have a single code that can do everything right. So in the UFS, on the ocean side, there are at least 3 codes that we're looking for. So we need to sort of think a little bit about, quote unquote, the philosophy of the UFS, and the fact that somebody says, I want to do research, and somebody says, I'm not ready for operations with that yet. There is no conflict there. It fits in a healthy environment.
Let us end this destructive conflict. So I don't want to be down on this. In fact, the angst in the room, the worry, the hair pulling. Step back. I'm going to come foot stomp what Hendrik said. This is the way the UFS is supposed to work. We are supposed to be fluid in considering innovation, right? That's what this conference is about, is innovation. Getting innovation into the operational systems. It's not like you make a decision and then you close off the ecosystem and we're done. So what we're seeing here is some of that turmoil, but the turmoil is exactly the way it's supposed to work. So I want us to be positive collectively about the way the process is working. It's not burden-free, it's not cost-free, we know that. But in the end, what we're doing here is going to advance NOAA's mission, period. Okay, that's what I care about doing. And the way that we're doing it right here is, to me, the most community-based, the most collective way that we could possibly do things, as long as we keep sticking with each other in looking at impasse or what have you. So thank you, Hendrik, for that comment.
Yeah, and to add one little thing to that, an argument for a scientist to make an improvement is not necessarily the same argument that is used for operations. So I see this in all the fields, all the time. I love the fact that the typical scientist wants to solve the problem for once and for all, right away, yesterday. In operations, Brian has to deal with the fact that if my model is just a little better in operations, I'm already served 1 or 2 lives. I'm going to wait 3 or 4 more years and let those extra lives be lost because we didn't make the small improvement to make the large improvement later. And so, so there are different arguments, including the ones about engineering. The fact that we want to get rid of a large number of codes that we don't want to have to port all the time, because if we do that, we cannot spend our time on getting out a better product in the middle and longer run. So it is kind of important to realize that a scientific argument is a completely valid argument, but it doesn't always follow exactly the arguments that we do in operations. For an incremental improvement will help save lives. If we delay an improvement, we don't help save lives.
Oh, we have another comment here. Go ahead.
Or I can speak loudly. I have a simple question. If RFS V1 goes in, do the legacy models go out?
Yes.
Maybe, I think there's an issue not only of when and how to stand down the legacy models, but the reality of whether you can even disseminate both concurrently to begin with. There may not be enough bandwidth to do that. So
if RFS V1 is not, we can't make a clear-cut case for RFS V1 over legacy models, do we implement RFS V1?
The answer to 99% of the questions in the world is it depends. I'll go back to the HAFS example. The decision to maintain HWRF and HMON was made pretty late in the implementation process. So right, we don't know. We don't know the answer to that question right now. What we do need to do is make very clear what the constraints are on the workforce, on the computing, and so forth in carrying forward those legacy systems or not implementing RFS v1 at all.
Hogging the mic for 5 minutes, and I apologize for that. But from an infrastructure point of view, it's going to be, you almost have to set up a separate standalone team to build the MPAS capability with DA, with the workflow, while people are working on RFS v1 and supporting legacy models. It's not going to be possible for the same set of people to do both.
And so the old gray man who's been there for a while, we've done this before. We've done this wrong when we tried to replace the GFDL hurricane model with HWRF. We kept modeling along, and it took us 10 years with two teams that neither of the teams were well enough resourced. We've done this with the GAPS v11. We had some downstream users that could not get off the GAPS v10. So we let the GAPS v10 in one member or on one cycle run just for one user or for one set of users. And so we've also, remember when we brought the FV3 into the global model, one of the arguments of the original plan was that the goal is not to have the new die core win out over the spectral die core. The goal was to be competitive and to be able to not have to deal with multiple models at the same time. So we've been at this place before. It's going to be a very interesting discussion, but it is not as it used to be in the good old JetBlue days that one person can veto whatever's going on and we're stuck in the old system.
Another comment from the room. Go ahead.
Yeah, Li Jiang from IM System Group. Just want to push the thinking a little bit wider. Is there a room for private sector or let the market decide? What I mean is that you have different user groups for different model output result. What I see today is that RFS is not a winner. Okay, it's not clear winner. There are clear advantage of MPAS and especially her version 4. Outperform RFS in many cases. So speaking of a broader picture of weather enterprise, how about let private sector work with research to run the non-EMC model, let EMC focus on the RFS? Would that help? Or would the market will ultimately tell you who is willing to pay what result or result combined? Just want to have that comment.
On this one?
Yeah, I am.
Okay.
So I just want to say, I think that's a good idea. I mean, IBM, if you've seen their presentations recently, I mean, they're doing some really interesting stuff with a small team. Of course, they've got a lot of resources and a lot of compute. And they have a very focused, almost ECMWF-like, precip and temperature, precip and temperature. I think that's a great idea because I think what IBM's doing is really interesting, and I think there's other people out there. I would just say that no matter what, I think there's an opportunity for doing parallel development efforts, but they've got to be funded, and there's not enough money, right? NSSL's asked for money for several years to look at some of these problems that I talked about today, and it wasn't high on the priority list, and I'm not complaining about that because there are a lot of other priorities here. We've asked for money to start exploring MPAS. The problem is that there's still a lot of people who believe in the orthodoxy that there's nothing wrong with FV3. I think we finally sort of made a better case in the last 6 months to a year. But at the same time, we can't expect progress with no money. And I think trying to figure out how to squeeze more out of the stone, which is what we're talking about, is going to be very difficult. I don't think people expect $1 million or $500,000 funding. But on the other hand, we always get there's nothing wrong with FV3, so this proposal gets chopped out. And that process is going to have to change, or at least that's why I think coming and talking is good for awareness. But I think even if we work with the private sector, which I think is good, we're still going to need some pittance of support in the OER labs somehow to sort of do this, because it's not like we're all standing around and we're all sitting on our hands, got nothing to do. So.
And there's sort of two conflicting answers to that question. Because the one answer is yes, hell yes. Sorry for the wording. This is exactly why we're doing open source and open science. And Enrique Alves and me and Arun and a few others published a paper in BAMS early this year on the benefits of how we got stuff from the private sector, from academia and others into operations for the WAVE model almost for free. So that's where we want to go. The flip side of that is go back to Steve Smith talk yesterday. For us, for the Weather Service, it is for a big part about equity in service and serving the entire population. If you allow industry and others to drive where we're going, that's going to the big market share of where there's money to be made. Are we still going to provide equity or not? I don't know. I just seeing. We haven't gone down that road yet. I'm just seeing a potential conflict. On the one side, yes, I do want everybody to contribute, but if you let this being run by where you can make money, do we still got the equity? And that's a conflict that we have to kind of figure out. Also, particularly for us in the Weather Service working in the public sector that have to support the entire community.
Minutes, I think, left in our discussion here, and I think getting to more of the community aspect, we've discussed quite a bit about what the operational plans are, but part of UFS is also serving that community, whether that be the private sector or university partners. So I didn't know if there was any other comments about using UFS for research and those needs there that anyone would like to make.
I think there is a need of USF to be used by the universities more, because the graduate students are those who use and develop the new schemes that are based on the recent experiments. So these students or postdocs implement the schemes, publish papers that create a basis for the new implementation operationally. I don't think that the development that they currently have in NCAR, for example, or NOAA, goes that deep into like specific cases to validate it. It could be, but I think the university development is really important, used by academia.
Thank you. Other comments, or has there been any new ones online that we've missed, or?
Okay, this one is, okay, yes, it's working now. It's been a stream of comments that have kind of come in online. I think some may have been addressed, but I'll just kind of go through them anyway. So there's a comment from Clifford Mass saying, moving to impasse would help bring NOAA and academic communities together. Huge positive. And then there's a couple from Lucas Harris. I'm going to kind of mention those two comments together. I think they've at least been partially addressed, but I'll go through those anyway. Again, it's about the NSSL presentation, saying that was critically flawed. GFDO plus CAPS presented results at NWP last week showing that precipitation and radar data assimilation issues are fixed. And then his second comment was saying that the results show no observations, merely that FE3 has a more effective response to shear and instability than ARW/CM1, which are nearly identical.
So let me address the first question. And I have actually interacted with the CAPS group in February about their data assimilation results, which were quite different than ours when we did this. And at that time, I found that they were actually using the temperature tendency limiter that's associated with the Thompson scheme, but at a value that was actually smaller, meaning more restrictive than the old HER limit And so what was happening, and I demonstrated this in a discussion, that their updrafts are actually half the speed of an unrestrained limiter run. So in other words, they're damping the vertical velocities in the model by quite a bit by limiting it as a 0.05 value. For those of you who remember, it was 0.07 in the HER, and I even showed in a paper with Bill Skamrock a couple of years ago that that value actually has a lot of impact on the storms, which is why we put this implicit vertical advection scheme in. So on that case, I respect the work that CAPS is doing, but I do think that they're using a very strong filter on latent heating that is basically reducing the problems that we would see in a free, sort of a more normal system. Regarding the observations, remember, I started out this talk, although it was a bit abbreviated, that I wanted to show that there's a consistent high bias in the FE3 model in the real data runs, and I tried to replicate that with a simple physics, and I think I showed that I did. So the point is that while there's no truth in these squall line runs, that's very, very correct. I think the behavior that we see in the squall line simulations are basically reflective of what the real data runs are, and I've tried to provide a hypothesis to explain why the FE3 is behaving the way they are. So I'm not saying that WRF and CM1 are perfect, but there's definitely a difference between the models, and that difference is reflected in the real data work. So on that level, I mean, I don't know how to really connect the two any more clearly than that. I'm sure there might be.
Thank you. Did we have other online points? We have a...
Okay, maybe. Okay, how's that? Okay, there we go. All right. Let's see. There's a comment from Youngjun Kim saying that the decision on whether and by when to keep legacy models is the question to ask the stakeholders, especially forecasters. And then there's another comment from Ben Liu, which may have been at least partially addressed, wondering if there are comprehensive or clean comparisons between the two dynamical cores, the FE3 die core and impasse die core.
Yeah, I think we partially addressed that one, or mostly addressed that one already with Lou's discussion. So was there another question in the room earlier? No? Okay. Oh, yeah, Pam. That way or this way?
For those of you who don't know who I am, I'm Pam Heintzelman, and I'm Lou's boss. I thought that would get more of a laugh. Okay. Adam's too, but that's not why I'm up here. I wanted to just kind of zoom back again a little bit to the conversation that we've been having about the kind of what drives decision-making in the implementation, which of course I'm not an expert on that, but I very much appreciate those challenges. And, you know, in the science, of course, that we are working to do to provide, you know, the best modeling capabilities to save lives, right? That's what I think we're all in the room here wanting to do. And so linking that back to the concept of letting go, like Frozen, of things, you know, that perhaps, you know, we don't need anymore, you know, be able to move forward so we have more of that bandwidth. And what does that bandwidth give us? It gives us the opportunity for advancement. And what is the advancement that we are working toward? It's probabilistic information, right? In order to better serve the communities that are out there, some of which are more vulnerable and need, you know, more time to respond, right? So that means we need adaptive information. How do you get adaptive information? You get that through probabilistic forecast information across scales, okay? And so I just wanted to kind of pull together some of the things that we've been talking about and think about, you know, that long-term goal and how do we get there with good science and how do we get there efficiently and effectively. And it's important that we have both the research side and the operational side, working toward that goal, which I think we are. And sometimes that there are difficult decisions, right? That requires, but it really is about getting the best science, the best information to all the different groups that we are seeking to serve. Thank you.
Thanks, Pam. That was really great comment. Probably getting towards our lunchtime here, so if there's any other really pressing things anyone needs to share. But I think that was a good way to wrap up is our big picture goal, like Pam said, of improving our modeling, getting to probabilistic to save lives and property. Great. So, well, thank you all for a great session.
Guys in the back, yeah, I'll deal with that.
be moderating today with Dr. Runchala. So thank you very much for joining us today. And the first presentation, just so we can start right on time here, is Edward Hartnett. Edward's been working on NCEP libs as well as a litany of other applications programs over the years. And yeah, thanks for joining us, Edward. And we're going to go over better compression of USF.
Hello, everyone. I'm going to talk to you today about some better compression features that have recently been added to the NetCDF libraries with the help of the community and NOAA. We added several new compression features to the NetCDF libraries, and there are three main new features. Parallel I/O plus compression works, and this has worked for some time now. There's a new compression filter called Z Standard, which is like zlib but faster. And there's a brand new feature called quantization, which allows you to achieve lossy compression with your floating point data. When you use these features, you get much smaller files and you get much faster I/O because you're moving around a lot less data. Since NetCDF 4.7.4, we've had parallel and compression working together. So if you're using parallel I/O, you can turn on compression with your data. It works fine. It works with these new features as well. The Z Standard library is similar to the zlib library, except it's much faster. So using it will get you better compression at a higher rate. And the new quantize feature with floating point data, which I'm going to explain, when you turn it on and also use one of the other compression methods, you get much better compression. All of these compressions are backward compatible with existing codes. In some cases, the existing codes may have to be relinked to the latest release of NetCDF, but no code changes have to take place in reading applications. This work developed over a number of years and has had a lot of support from the community. This work started in 2016 or even earlier with Charlie Zender at the University of California. He is associated with the CMIP archives and is very interested in compression. And he's also the author of the NCO, NetCDF Command Operator Tools, which do a lot of compression work. So he was using a lot of advanced compression technology. Here at NOAA in 2019, Jeff Whitaker put in the bit shaving into the atmospheric model and reduced 36 gigabyte file. Things advanced until in 2022 we released NetCDF with these new features available. And I'll describe them all a little bit more. Talk about parallel I/O with compression. This was in NetCDF 4.7.4, so it's been out for a number of years. And the Unidata team here in Boulder did us a big favor by doing a quick release, allowing us to get this in UFS-16. So the chart over here shows, and it's from a paper of June Wang, it shows the different sizes and write times for a very large file with different compression technologies turned on. And we see on the far left there, using binary writes, it took 79 seconds on the far, and it was a 33 gigabyte file. And on the far right, after a lot of tweaking with settings, it's down to a 6 gigabyte file in 34 seconds. So that's a sizable improvement. What I wanted to point out on this slide is if you look at the last two on the right, where it goes from 43 seconds to 34 seconds, the only difference there is the chunk sizes. When you're writing NetCDF4 data, the chunk sizes are very important for performance. So you see that by changing the chunk sizes, they were able to achieve an additional 25% improvement in their performance. So that's something you should watch out for. Okay, let's talk about Z-standard. Like zlib, Z-standard is lossless compression. If you turn on Z-standard and write your data and then read it back in again, you'll get the exact same bits that you wrote out. It works on all platforms. It's very widely available. It's much faster than zlib. And not just writing, but also reading or uncompressing is much faster than zlib. Zlib is 25-year-old technology. Z-standard is much more modern. It was written for high performance, and it does a great job. In zlib, there's a number there's a setting that goes from 1 to 9, but it pretty much is pointless to set anything other than 1. Okay, if you could change it to higher settings, it'll slow down, but it won't compress any better. Z-standard gives you a much better trade-off there. So if you really are in a hurry and you don't want to compress so much, it really works to change that number. And what you see there in that chart, we changed the UFS to use Z-standard, and we ran these tests and measured the time it spent writing out data. And the time on the far left, the blue column, that is with zlib, which is the current state of play. And the one on the far right, the green one, that is with Z-standard. And you can see that in almost every case, the write time is almost 50% less using Z-standard. And that is the only change in these runs. So it's faster, is the point. Whoops. So how do you turn it on? It's very simple. In your NF90 def-var statement, there's a new optional parameter, Z-standard level, and you set it, just like that. 4 is a good starting point. Okay, if you try and use both Z-standard level and deflate level at the same time, you will get an error. Just one or the other, pick one. Okay, that's it for Z-standard. Let's talk about quantize. So the point of quantization is you have floating point numbers and you're preserving many bits more than are scientifically interesting or valid. Because when you have a 32-bit floating point number, it saves something like 8 decimal points, and that's more than any of our quantities generally are really valid for. So what quantization allows you to do is specify the number of significant digits for your floating point variables, and then bits which are not required to maintain those digits are smoothed away. And when that is done, the data compresses much better. So here we see an example with the value for pi. And the very top value there is the value for pi as a 32-bit floating point number. And then we apply successively less and less number of significant digits, and you can see how it affects the significand by having zeros pile up there on the right. And when you get down to number of significant digits 3 or 4, you see there's a fairly sizable number of digits there, and they all compress away. So that's what it does. It works well with the fill value. So whether you're setting your own fill value or you're using a default fill value, it will not try and quantize fill values. It does add an attribute to the variable saying what you've done, because if you did not add that, there'd really be no way to tell that you've done this to the data. And this data is then completely backward compatible to all existing NetCDF applications. They don't have to upgrade in order to read this data, just to write it. There's 3 different algorithms you can choose from. If you're unsure or you're just starting out, go for the middle one, granular bit round. It's the most aggressive and, 2 minutes, good. Bit round over there allows you to specify the actual number of binary digits that you want to keep. Oops, I keep hitting the wrong one. How do you turn it on? Very simply, in the NF90 def-var statement, there's 2 new optional parameters, quantize mode and number of significant digits. Set them like that. Best results, if you use these features together, you can achieve significantly better compression faster, and that will result in much better I/O times. What you see on the right there shows the final compression ratio, which is what you ended up squishing the file down to, essentially. And If you look at the colored bars on top, you can see that using quantization significantly improves your compression. NetCDF does require some extra help installing to make sure that you can read and write Z standard. And essentially what that is you have to worry about this with plugin directory option. You have to set it, and then you have to set it as an environment variable later when you're using any of the plugins. That's a part of HDF5. When you do configure and build NetCDF C and Fortran, you get these configuration summaries, and I just wanted to show them because at the bottom you can see the compression options, yes, meaning they're turned on. You want to check these, make sure you've configured it right. Okay, and this is my final slide. I wanted to mention, I don't usually mention that all work is unit tested because it just seems like that's obvious, but it's not obvious, I suppose, to everyone. So all of this work was unit tested and is unit tested, and it would not in any way, shape, or form have been accepted by the NetCDF team if it did not come fully provisioned with unit tests. And unit tests is one of the things that they inspect first to make sure that it's adequately tested and adequately functioning. Thank you. Any questions?
We were told to, if everyone could save their questions for the joint session at the end of the day, please.
The next screen, thank you very much for that. Next, we have Dr. Oliver, who's a computational physicist at GFDL, while they pull the slides up. Virtual, okay, perfect.
All right, hello. Can everybody hear me all right? I think we should be okay. Okay. All right, thank you, everybody. Yeah, my name is Oliver Albert. I work at GFDL as a computational physicist. Sorry I couldn't be there with you all today, but I'm really excited to talk about the PACE project and the PACE model that we've been working on for a few years using GT4Pi in order to port the FE3 GFS model into Python and run it at high performance on CPU machines, as well as GPU machines. So to start, I think a lot of you probably already know this, but I'll give a brief bit of background and motivation for this work. On the left here, you can see the number of accelerators that are being used on HPC systems in order to improve performance. And as we move into the exascale era, this has only increased, especially at the high end. On the right of this slide, there is the top 10 fastest supercomputers in the world, and you can see almost all of them are accelerated, usually with GPUs. And so in order to harness these systems' power and increase resolution, increase ensemble size, or just reduce the compute time to run on these systems, we need our models to be able to run efficiently on GPUs. And so there are a couple of different approaches to doing this. One is just to take the model, rewrite it in CUDA, or HIP or whatever language for GPU programming you like. This is obviously very good in terms of giving you control over what's happening, letting you have the most granular and easily accessible optimizations at your fingertips. But it does mean that you have to write CUDA code, which is not really designed for scientific computing. And also it means that now you have your Fortran model to run on CPUs, you have a CUDA model to run on GPUs, and that's just a nightmare for maintenance and model development. Another approach is to use compiler directives like OpenACC, similarly to how you use OpenMP in order to parallelize with multi-threading, or to use multi-threading to increase performance on a CPU. And this obviously lets you keep your Fortran code, which is very nice, but it can be a little awkward in terms of the optimizations and your increase in code complexity by having these different if-def blocks around for CPU versus GPU, and you still may have some duplication. So on the right of the slide, here's an example where we have a model that has one COE-TH implementation for GPU that's been optimized for a GPU machine, and a separate version that's been optimized for a CPU machine, which comes up because maybe you need to do have a different memory layout, or you need to slightly order some of the calculations slightly differently just to preserve your cache. And of course, with both of these options, writing in CUDA or using something like OpenACC, if in 5 or 10 years we're kind of having the same conversation, but with TPUs or FPGAs as the latest hardware acceleration targets, we're back to square one, right? So that brings us to the third approach, which is the one that we've been using at GFDL and that I personally, to put my cards on the table, prefer, which is to use the domain-specific language. And the domain-specific language is a programming language that, as the name implies, has been tailored for a particular application or a domain, similar to how, like, TensorFlow is a GPU or is a DSL for running and building machine learning models. And TensorFlow is actually a really good example because it's very analogous to the DSL we're using, which is Grid Tools for Python, where you write your code in Python using this GT4Py library. But what is ultimately run is not necessarily Python code. You can run Python code with GT4Py, which is very helpful for developing and debugging your model, but you can also pass through a much more complicated tool chain where the code is translated to C or to CUDA, I guess C++ or CUDA rather, and optimized and then compiled to run at very high performance on a CPU supercomputer or a GPU supercomputer. GT4Py is open source. We encourage everybody who's interested to become a part of the community and also to check out Christian Kuhnlein's talk Thursday morning, where we'll go into a bit more detail about GT4Py and about the effort at ECMWF to use GT4Py for their next generation modeling. But so we have this DSL. So we used it to make a model. We called it PACE. PACE is not an acronym for anything. It's just a word that we liked. It's our port of FE3 and currently version 2 of the GFDL Cloud Microphysics. The rest of the GFS physics has been ported into GT4Py, but hasn't been fully optimized or integrated into the model yet. PACE is also open source. I really want everybody here to check it out. Fork, test, contribute to PACE. If you're interested in some of the details, the paper that we wrote on the model was published in May and was actually selected as an editor's highlight in GMD. So you can also read the paper, but wait until the end of the session before you run out and do any of that. So obviously this is a port of a Fortran model. We can compare our code against the Fortran, which is what we're looking at here. On the right-hand side of the slide are comparisons between the Python and Fortran code running the Moist, Jablonowski, and Williamson baroclinic instability test. Just looking at 850 millibar temperature here, but it's pretty similar for whichever diagnostic variable you choose to look at. And during the steady state phase, during days 1 and 3, the error the differences between the models are extremely small, right? 10 to the minus 11 Kelvin. And as we develop the instability and integrate for 9 whole days, we still only have differences of about half a Kelvin at worst. And if you think about like how floating point arithmetic works and how there are different implementations of, transcendental functions, some different order of operations, just like plus minus, depending on what the hardware backend is. We're very happy to have that level of agreement after 9 days of integrating a fairly divergent test case. But of course, the original motivation for this was performance. So if we look at the performance, this plot is from actually this is originally from the supercomputing paper we had published last year as well, and was reproduced in the PACE paper. It shows our weak scaling results, both for PACE as well as the Fortran code, going up, in this case, to half of Pitstein. And we have a consistent 3.5 times speed up over the Fortran running on Pitstein's P100s. If we run on A100s, we get even more performance just because it's a newer chip. And also, I just want to call out that PACE weak scales incredibly well, as does FE3, to be fair. But the performance really is, I think, key for motivating a lot of this. We haven't done any CPU performance engineering yet. We have some preliminary results from some initial work, but currently the main branch of PACE is about a factor of 4 slower than Fortran. But like I said, we have some preliminary work that's been done that is very promising, and we should be able to get parity with the Fortran code fairly quickly. If you want more details about the actual backend and performance optimizations, you can check out the supercomputing paper linked both on arXiv and at the supercomputing website here. But one other thing that I think is important to highlight, especially here, is a lot of the advantages that Python as a front-end language brings us, right? So because we're running in Python, or we're building a model in Python using this DSL as a library, we have access to the entire Python ecosystem, all of these community packages. We have PDB available for debugging. We have PyTest available for CI and for unit and integration tests, which is how we were able to validate all of our model code. We also have access to Jupyter notebooks, which I think are incredibly useful just as a pedagogical tool and as a model development tool. So you can run PACE from within a Jupyter notebook. You can also run PACE components within a Jupyter notebook. So that's what this Jupyter notebook on the right here is. It's taking the tracer advection from PACE, from FE3, initializing a wind field, and then running tracer advection for 10 acoustic time steps. And then at the bottom, you can see the initial tracer concentration, final tracer concentration, and the difference. And this is really, I think, incredibly useful just for teaching people how the model works, what the different components do, and also for prototyping new model components, new tracer advection schemes, new subgrid reconstructions. And yeah, I just wanted to highlight that. We also have access to a bunch of other tests that we can do that are extremely difficult to do in Fortran, like taking the dynamical core, advancing a time step, and then checking to make sure that all of the internal variables are correctly being reset to 0 in the interim. Yeah, Python as a development and scientific coding language is incredibly useful. Obviously, there's still work to do. I mentioned that we don't have all of the GFS physics schemes fully integrated yet. We also have the latest GFDL cloud microphysics that we're finishing up the port of, CPU performance, obviously. We are currently working on adding the ability to have nested grids and doubly periodic domains. All of this is funded by at least on the NOAA side, by the Software Engineering for Novel Architectures project. So I'd like to acknowledge them here. But all of this is ongoing. All of this is something you can contribute to if you like, if you are interested in model development or in any of these technical aspects. And I very quickly threw this slide together during the break, highlighting some of the things that have been repeated topics of discussion so far in this conference. But PACE is portable, it is fast. You have Docker support. We have, very good uses in terms of both as a teaching tool for research and as a component of your forecasting model. CI is very easy to do, again, using PyTest, among other things. And because we're in Python, it's very simple to integrate with any pre-processing or post-processing workflows that you have. So I want to encourage everybody to check out the repository, test it out for yourselves, contribute, get in touch with me, please. And give it a shot. So just at the very end, I'd like to use my last 10 seconds to thank the former members of the AI2 DSL team, where we did a lot of this work. And I'd like to acknowledge our partners at NASA, who have also contributed a lot to this effort and are still contributing a lot to this effort, as well as everybody who's worked with us at AI2, at the Swiss National Supercomputing Center, ETH Zurich, UW, and Meteo Swiss. And that is time, just about.
Okay, thank you very much. While we pull up the next slides, if you have questions, again, we'll please save them until later. We have the director of the JCSDA coming to talk to us about the next generation of DA.
Hey, good afternoon. My name is Tom Molinier, and we're going to talk about JEDI. And we've already had some conversations about JEDI, so hopefully everyone is interested and curious. So that one slide about the Joint Center, it's a multi-agency partnership. We have NOAA, we have NASA, Air Force, Navy as core partners, and fairly recently we also had the UK Met Office and NCAR becoming observers in that partnership. And we're really about research to operations and operations to research. We have a distributed staff with core and in-kind contributors in our annual operating plan, and we're really committed to the critical path to operations. Just one slide to remind all the stuff that was done by the Joint Center over the years in terms of trailblazing, community development, with hopefully now fairly standard working practices, but basically back then, quite innovative in terms of agile project management, and you can read the metrics. We have more than 1,000 activities on boards per week, open science with million lines of code that are open source with quarterly releases. So this is the list top right here of the releases over the past year. 24 repositories are involved in these releases, but we're also working closely with EMC and EPIC on SPAC Stack that has, to my knowledge, hundreds of packages in there as well. So it's really working nicely. A lot of automated testing. We have hundreds or thousands now of tests. And heavy use of cloud computing and containers, and including containers developed on a large number of nodes with high efficiency. A shift in paradigm for the software portability. We make it a requirement in the design rather than an afterthought. So what used to take many months to port now basically takes hours or days. And that is because basically the work is done upfront to make it portable. We're supporting right now 12 different HPCs in NOAA, NASA, DoD, academia, but there's actually a lot more than testing. And also an effort on community training. We have online tutorials, we have our forum, we have our documentation, but also had JEDI Academy's week-long training where we've trained about 35 universities and partners and international collaborators as well. Now, where's the... There we go. All right, so JEDI, this is basically, first and foremost, a consortium of jointness, trying to share as much as possible, but without actually imposing a single approach. Another way of looking at it is we want to allow as much scientific diversity as possible, but we definitely don't want to waste resources in reinventing the wheel. So it's meant to be a unified DA for the Earth system science, from bridging research and operations, and looking at scientific productivity through modular code, generic programming, separation of concerns, so adopting modern software standards. The figure on the left here is a diagram showing the different deployments that are actually actively worked on, and it might not be, there's probably more, and it might not be completely up to date, but there's actually a lot of JEDI data simulation systems that are being developed in parallel for various applications, for their different partners as well. The real metric is seeing how much code is reused across these different applications, because if we keep reinventing the wheel, we haven't gained anything. But if we don't, then there's a huge multiplying factor. So if you look at the bars on the right-hand side, the first bar is actually the global GFS, FV3 GFS, and we have exactly the same interface with GEOS at NASA. The second bar is so I should say what the bars are about. There are actually a number of lines of code to assemble the executable for that application. And the colors are basically, the blue ones are these open source packages that we use, mostly borrowed from ECMWF. The greens are repos that are open source that we release, and the red are the model interfaces. So all the blue and green is actually generic reused, is the same across these different applications. The red is model specific because it's a model interface to JEDI. And so you have global atmosphere at NOAA, NASA. Then second bar is global atmosphere at NCAR with MPAS. Third one is the marine DA, so MOM6, SI6 for ocean sea ice. And last one is the NOMP for the National Water Model. So what you see is actually the specific code that cannot be reused, that is very specific to a given model, is a really small fraction of the overall software, which is a great win. Hopefully that starts to address some of the questions earlier on. Where are we in terms of the maturity of the development, and what are the plans to actually transition this to operations? So phase one is actually, the goal is to match the existing skills of operational systems. And we're actually, we're not there yet, but we're pretty close. And so, in terms of notional timeline, I say notional because I don't control these timelines, and I don't want to commit anyone to these timelines. But basically, this is the latest information I get about the deadlines for code freezes, so that the TTO process can be put in place with various components for the atmosphere, the marine, the land, the aerosols for NASA, NOAA, Neptune, Navy, Met Office, Air Force. So it's coming up pretty quickly, and in terms of qualifying observation operators, QCs, background error covariance matrices. I'm not going to show you all the details here, but there's a lot of maturity and still a lot of work to do. But there's definitely many teams working on them in parallel and collaborating. What's also very exciting is we're not investing all of this just to reproduce what existing operational systems are doing. We're actually going to leverage a lot of new capabilities. One of them is just the idea that now you can have a system that can handle the various components of the Earth system from a unified standpoint. So this is something that we actually put in practice with Skylab. So this is just an example that you can actually look a lot more on our website through our Skylab viewers. It's at skylab.jcsda.org on our website. And these are just examples of various observations that are being assimilated. So the idea with Skylab is it's actually a quarterly release that gets a snapshot of all the latest developments that you got, and that we actually exercise in these experiments where you have the atmosphere, the aerosol, the trace gases, the land surface, the ocean, and the sea ice, all handled through that unified end-to-end system. So that end-to-end system has a data pipeline that uses YODA as a way to have a common dictionary to qualify the observations and the and the metadata. It puts this on a data store that we call R2D2, and has a build system that can actually configure the application to your given system, and the workflow manager that's called EWOC. Then we put these diagnostics on our website that you can then use to inform on various scientific priorities. And it can be configured for various models, for various applications. By design, it's a flexible system that can run on multiple platforms and multiple applications. Here's an example with the UFS atmosphere cycled in over a month. You can find our website by using the little top left toggle here. You can swap for aerosols or marine as well. And have a look at this. All that code for actually generating these experiments is all public. You can download it today. The latest release was done last week. So where are we heading with all this? We have these three major goals that intersect, luckily. So we want to support the agencies to transition to operations. This is a very top priority. So really system hardening and coarse scientific quality assurance. I say coarse because there's a lot of fine-tuning that happens for each specific agency that's outside the scope of the Joint Center. This is not joint, it's specific. We also want to actually use all the agility and the flexibility of the system to rapidly integrate new innovation, and there's definitely a lot of great ideas we can bring in, and we're eager to do. And we also want to train the workforce and engage the community and use this as actually a teaching tool. So can JEDI be used for teaching? I certainly hope we manage to get that. So how do we reconcile these three pieces? I'll hopefully make Mike happy by actually saying we can actually do this through a hierarchical system development approach. So if you think about, the cost of running experiments, you can think like an operational grade experiment is very expensive. It requires a lot of CPU hours on a expensive HPC. On the other hand, you can run with a toy model, a very low resolution model on your laptop. And of course, there's things in between. Maybe you can use the cloud. Maybe you can use your own clusters, basically. So if you think of actually using that hierarchical system, you can actually start having a hierarchy of configuration and use the flexibility of the Skylab end-to-end system to actually sort of bridge these different levels here. So we have that Skylab Large, which is basically our demonstrator that you can find on our website that runs on HPCs. It runs in the cloud as well. Actually, the last one was running on AWS. It's basically a point of convergence for prototyping and having a continuously running prototype that's gradually getting really close to operational grade that our partners can really use for transitioning to operations. So it's the idea of a concept car that you use for testing all the pieces, and that can be transitioned to a production car. Then in the middle, we actually introduced in our science workshop a couple of months ago the concept of experiment as a service. So basically, that end-to-end service that we're planning to release fairly soon if we have the right resources to dedicate to this, where basically you have all the data available, you have the build and workflow available, you have the experiment configuration manager available as well, the diagnostics, and it can run on pretty much any platform that you can think of at the moment. So that's basically for the community to being able to have actually means to be running Skylab and do very scientific relevant experiments that can directly be anchored in that large experiment that I mentioned earlier. But at the same time, let's be honest, most of us here won't have the resources to run an operational full-size, full-resolution version. So it'd be at a low resolution with basically sort of emulating the full system. And finally, the JEDI EDU is like a Skylab Small. It's a very low resolution model, or it can be also a toy model that you can actually download on your laptop, and that can be actually integrated in teaching in university curriculum, for example, that we use for our Jedi academies for teaching DA. So we've been working so far on prototypes with Colorado State universities. They tested this with students, had real great feedback. We definitely want to expand on this with a lot more in the community. So if you're interested, please reach out. This is my final remarks. So basically, we're using the requirements of the Joint Center, this requirements of jointness. We're turning this as actually an asset by focusing on joint problems and really bringing that multiplier effect to actually get a lot of value out of this. We have a lot of commitment from various agencies listed here, and we're getting really close to operational implementation, as the notional timeline showed. And it really will unlock a lot of new transformative technologies to be transitioned a lot faster to operations. With that, I'll just let you read our vision of success for the next 5 to 10 years, and I'll take any questions you have. Thanks. Thank you.
Okay, thank you very much. I guess we're going to still save questions for the end. So our next guest is Dr. Arun Chawla, who is is going to talk on UFS, and we're looking forward to model infrastructure. Thank you.
Thank you. All right. Getting trolled by my boss. That's the way to do it. Yes. Hello, everybody. My name is Arun Chawla, and I'm going to talk here about work that I have not done, but my people that work at my team have done, and with the partners around. So if I mess up, it's on me. Yes. Anyway, so here's a basically overview. We're going to talk about our modeling system, which is the UFS weather model. The UFS weather model is the core model that defines what goes into GFS, GEFS, HAFS, RRFS, and soon to be seasonal forecast system. So we have all these different applications that run it for different configurations, but they run the same underlying core modeling system. And I'm going to give you an overview of what developments have been made in the last 4 to 5 years in building this modeling system, and its computational performance. And at the end, I'll end with open source and open development. Okay, so this is the modeling system. It is a fully coupled system. It's connected to 17 authoritative repositories. There's a big umbrella repository for the UFS weather model. It connects to 9 major flagship model components. Each one of them are open source repositories by themselves. We have made it a requirement that anything that we work with will be open and available for the community to see and use. There is a community mediator, and there are shareable nuopsy caps that we use for all of these components. The model infrastructure is basically been developed to build a unified system. You can run it as a fully coupled model. We're running this for the GFS v17, the GEFS v13 that's coming up, the current RRFS v1. We've got an AQM air quality model that's coming out of it. HAFS version 1 was put in operation, and we've got the FE3 Jedi, and we've been using Marine DA with this modeling system. All right. And so here, the community mediator, we used to have an in-house NEMS mediator that we transitioned away from, and we've gone to what is a community mediator. It's much more modern code. We share that with the CESM group. They use the same mediator. It's essentially, it works for both the CESM model and the UFS model. The UFS itself has 2 configurations, one for HAFS, one for the rest of UFS, because in HAFS, there are domains which are not exactly overlapping, so we need to have some tricks we have to do for coupling stuff there. And the graph that basically the plot basically shows that the difference between CMAPs and NEMS is about the same order as when you ran NEMS on 2 different computers. So essentially, it's the same thing. Right. So order of organizations is, and nothing happened, and nothing happened. Wait. Am I frozen? Okay. The other new thing that we've got is the community data model, the CDEPS, which is a community data model. This again has come from the CESM group. This used to be part of the CESM workflow, which is now the name is SEAM. Yeah. Right. And they took it out of SEAM and created CDEPS as a separate component so that we could also use it. Essentially, it allows us to put different data models, and we can use a data model for the atmosphere, the ocean, the ice. We can create a data model for the wave. We use it to do testing for individual components. We're right now using it to run the data model, data atmosphere, MOM6, size 6 to do ocean DA work with this configuration. We've also had air quality models that we've integrated with the coupled system. To the left is the CMAC model that was added to the UFS weather model. This is going into operation in a couple of months as AQM version 7. To the right is essentially the aerosol model that is the FE3 that is the go-kart model that was basically used by NASA and us jointly. And that's going to be part of, I believe, still planned to be part of FSV13 as a fully coupled aerosol model that's added to our system. The other work that was done was for the NUOPSI cap for WaveWatch 3. It used to have a grid-based NUOPSI cap. We converted to a mesh-based system so that we could have unstructured grids. And we're using this to couple it through the CMAPS mediator. Again, it provides restart reproducibility for the wave model. And we're also using this to have a global unstructured WaveWatch 3 model for the GFS V17 that will allow us to have a much higher resolution all the way to the coast, and also allow us to, to let the wave field to be continuous across the MOM6 tripole scheme. And so, just to give you an idea, the UFS weather model has a build system that can be built into multiple different configurations. You can build it as a fully coupled model, which will allow you to run, the different ocean models. You can have a halves configuration, which will couple a HICOM ocean model, but not the MOM6 ocean model. Or you can have just a ocean DA system, which will just connect MOM6, size 6, CDEPS, CMAPS, and all of that. All of this is with CMake, and you can build several executables simultaneously. And the last work here is a collaboration that was done with 4 different organizations. This is the moving nest capability. The GFDL developed the telescopic nesting capability. AOML built the moving nest to this telescopic nest, and EMC and NCAR worked together to do the asynchronous I/O so that all these moving nests could have their, the I/O part to be done asynchronously with the right grid, so it'd make it pretty fast. We also added inline post, essentially, which allows us not to have to worry about writing out, and we drop. Earlier, we used to write the model output in history files and then run a post processing to create the post. Now we write post as a library that is just provided during runtime. We get the post processing directly outside. It saves us about 80% computational time for higher resolution runs. It's been very useful when we were doing the RRFS runs on the cloud because we reduced one set of I/O operations. And it has also been extended to the multiple grid moving nest capability, and it's being used as part of the HAPS implementation and operations. This one test, I think you already saw this plot with Ed's talk. We wanted to do this implementation for GFS V16. I think we were doubling the layers to 127, and then when we went and told NCO that we're going to be having 33 gigabytes per file, I think they started laughing for a while and said, yeah, get out of here. So we had to work with the Unidata team to change our entire data format. We went from NEMS.io to NetsADF. I think Ed was part of that team. And we went from, through various configurations, we went from writing 33.6 gigabyte file in 79 seconds to 6.3 gigabyte files in 34 seconds. And without this development, we wouldn't have been able to get this into operations. And this, again, is the kind of stuff that really helps to have community development, because all of this was done in 2 months. Unidata did releases of NetCDF to meet our requirement. Ed actually worked to put together testing infrastructure so they could test GFS-like output files so that Unidata could have that capability in there. So I really appreciate that collaboration. I was wondering where that went. All right, so this is the last plot that if it plays, may play, but anyway, the UFS weather model is essentially an open development model concept that we've had for the last 4 or 5 years. It has 200 forks, over 140 developers. We've had greater than 1,700 issues. We have 4.3 miles lines of code. All of this has happened in the last 5 to 6 years. We couldn't have done it at EMC alone. And essentially, we have been able to do this thanks to the collaborations with everybody in the UFS community. And there was a very nice graphic which refuses to play. It's, but anyway, it's yeah, maybe I'll show it to you guys later. But the point that I want to make is that, we have had the kind of features that we put in together here. We would not have been able to do it if this was a closed repository. This has been work that has been done not just by EMC. EPIC's doing a lot of the code management of this now. Development happens from all parts of the organization. There are folks from GFDL who have contributed. There are folks from GSL, PSL, all the labs. And so we really appreciate the collaboration. So, all right. But by the way, if you ever want to see that animation, it's pretty neat, and Sam Trahan has put together the software for it. So if you want to do it for your repository, it looks pretty good. And it's available on GitHub, so if you want to play with that. So in summary, this is the coupling infrastructure that has been developed to support the UFS weather model, which is a fully coupled model that supports all our applications. It is built consistently with various different configurations. It has got a CMake build system. We put a lot of effort in I/O performance. Ed's been very critical in helping us build the capability to have things be compressed, written parallelly. And the UFS weather model is open source and open development through collaboration with community, and everybody's welcome to join and contribute and play with it. So thank you.
Thank you very much. Next, we have Youngming Wang, who is a research scientist at Oklahoma, while they pull the slides up.
Hello, my name is Youngming Wang. Today, we would like to introduce our recent work improving CONUS convective scale forecasting with simultaneous multi-scale INVA data assimilation. I would like to thank my co-author, Professor Xuguang Wang at MapLab School of Meteorology, University of Oklahoma. As we all know, an accurate convection allowing prediction requires a convection allowing model to not only properly resolve the convective storms, but also the large scale environments. In addition, over the CONUS domain, various observations like in-situ observations, satellite readings, and radar observations are available to sample multiple scales. Therefore, multi-scale data assimilation is required to accurately estimate the atmospheric states from synaptic scale to convective scale by properly extracting information from all available observations. Earlier studies have developed the simultaneous multi-scale DA to simultaneously update all result scales by assimilating all observations at once. Such simultaneous multi-scale DA was developed in both EN1 and pure ENCAF. These studies enable simultaneous multi-scale DA through implementing a scale-dependent localization in model space. Additionally, we further developed the simultaneous multi-scale DA through integrating scale-dependent and variable-dependent localization. Our study revealed the critical impact of SDR and VDL on convective scales. However, we only explored their impact using an isolated supercell storm and mostly through the assimilation of radar observations. Limited studies have implemented and evaluated the simultaneous multi-scale DA with both SDL and VDL on CONUS convective scale forecasts. In this study, we plan to implement and evaluate a simultaneous multi-scale DA system with SDR and VDL for CONUS convective scale prediction with various observations. Through this study, we also will understand the impact of simultaneous multi-scale DA on analysis and forecast of CONUS convective storms from the physical understanding perspective. This study is performed using the May 3rd, 2018 score lines. The model domain covers the entire CONUS. In this table, the model configuration is summarized. Both conventional in-situ observation and the radar reflectivity are assimilated every hour from 19Z to 0Z. 18-hour free forecast is launched from the final analysis. To evaluate the implemented simultaneous multi-scale DA system, 2 experiments are designed. Baseline used a similar approach with operational system where in-situ observations and the radar reflectivity observations are separately assimilated. The second experiment is the implemented simultaneous multi-scale DA with both SDL and VDL to assimilate both in-situ observation and the radar observations at once. The used localization radius are shown in this table, particularly for simultaneous MDA. Hydrometeors and the vertical velocity use a stricter localization radius than the remaining variables in each scale. During the DA cycling, the priors of simultaneous MDA red line here better fit to in-situ observations and radar observations than the baseline experiments, the blue line here. These sawtooth results indicate that simultaneous multi-scale DA produces more accurate multi-scale analysis, and its advantage can be maintained in the subsequent one-hour forecast compared to baseline. The convective scale forecast showed that the simultaneous MDA, the red line here, outperforms the baseline experiments, the blue line, for composite reflectivity in the majority of forecast leading times. Simultaneous MDA also yields more accurate forecasts of winds, temperature, and moisture fields than baseline in the majority of forecast leading time when verifying against the in-situ observations. The improvements in convective scale forecast by simultaneous MDA over baseline are achieved by the improved reflectivity, coverage, and organizations. Additional experiments are designed to examine the hypothesis that simultaneous multiscale DA can more effectively extract information from radar observations and in-situ observations to update all result scales. MDA radar is the same as the baseline experiments, except using the same configuration as the simultaneous MDA to assimilate radar observations. On the other hand, the MDA conventional is the same as the baseline, except using the same configuration as the simultaneous MDA to assimilate in-situ observations. To understand the improvements in analysis and forecast by simultaneous MDA, analysis difference of each experiments with baseline is shown in these slides. Results show that the large analysis difference near the front and along the drawing line are also obtained in the MDA conventional experiments. On the other hand, the larger analysis difference associated with the code pool, with the code pools and the inflows are also generated by assimilating radar observations. The differences between simultaneous MDA and the baseline can be partially attributed to the combined effects of MDA radar and MDA conventional. In the subsequent forecast initialized from the third G cycle, simultaneous MDA has the substantial forecast than baseline, the red line, compared to the blue line here. MDA conventional and MDA radar have the forecast scales between simultaneous MDA and the baseline. Compared to baseline, MDA radar and the simultaneous MDA improves the bow echo structure and the storms over the central Oklahoma and northern Texas. MDA conventional and simultaneous MDA enhances the northern storms and storms over central Oklahoma and northern Texas. First, we introduced the ability of MDA radar in extracting information from radar data assimilation. Compared to baseline experiments, MDA radar and simultaneous MDA produces stronger and broader code pools. These stronger and broader code pools in MDA radar agree better with the observations than the baseline. The same conclusion can also be applied to the moisture and wind. And winds, these differences are achieved by the ability of MDA radar in producing larger scale increment in compared to baseline. This result is consistent with these earlier studies. In these slides, we introduced the ability of MDA conventional in extracting information from the in-situ observations. The remarkable analysis difference between multi-scale conventional and the baseline mostly match with the locations where small-scale covariance are dominated the full-scale covariance. Compared to baseline, MDA conventional better maintains the drawing line in both analysis and first guess. These improvements are obtained probably either by reducing noisy distance correlation or by alleviating the overestimated area coverage or moisture increments with the use of a strict localization to small-scale covariances. In summary, simultaneous multi-scale DA system with SDR and VDR for corners convective scale prediction is implemented to assimilate virus observations and evaluated using the May 3rd, 2018 score lines. Comparisons between simultaneous MDA experiments and operational like baseline experiments suggest that simultaneous MDA produces more accurate analysis and convective scale forecasts than baseline experiments. Simultaneous MDA experiments obtains improved convection favorable conditions along the front, the drawing line, and the surrounding storms and cold pools compared to baseline. Diagnostics show that the improved conditions near the front and the drawing line in simultaneous MDA are obtained by eliminating noisy correlations with the assimilation of in-situ observations. The improved conditions surrounding storms are associated with the assimilation of radar observations by keeping larger scale increments. Our EMC collaborator, Dr. Sho Yokota, is testing this simultaneous approach for roofs towards potential roofs version 1 implementation. These results in these slides were obtained within the GSI framework. We are also working on developing the simultaneous approach within JEDA. This is a prototype we are using for both regional and global applications using JEDA. Thanks to Corey for developing this. And here is an example. We examined JEDA using hybrid and 3D methods. That's all my slides. Thank you.
Okay, thank you very much. Next, we have Dr. Christina Holt, who leads the Unified Workflow team for EPIC.
Thank you. I am going to be talking about our effort on the EPIC Unified Workflow team to do just that, unify the workflow for the UFS applications. Here I'm listing several of my Spring team members, but notice that we do represent a variety of different organizations on the team. And I say Spring team members because our team has gone through a variety of transformations over the years that we've been at this. And I can do this. Can I do this? There we go. And that's been a collection of folks all the way back to a UFS R2O project started with Ben Cash. Raul and Arun have been there with us from the start in this progression of the team. And then just a long list of additional contributors. I've starred the ones who are still with us in our summer team. And that, I think, is starting to settle down now, as a lot of these have recently come on as full-time team members instead of more of the transient in-kind support that we've had through a variety of different iterations here. Here on the left, you can see that there are several different in-kind resources listed here, from EMC to GSL and series, GMU. DTC has provided some in-kind support here as well. EPIC came in with contract support. We have support on the team from the JTTI and also the software engineering for novel architectures project at GSL. And then we have a stakeholder group that provides really nice input on a regular basis from a whole variety of institutions there as well. I won't repeat this. We're all here about UFS, and took this directly from the website, but we know what we're here about, and we've done a lot of this really well, I think, covering a whole variety of components and modeling coupling tools and all of that fun stuff, down to that last little bit of the sentence of workflow software, where we haven't quite unified just yet. And I just want to iterate that we are all running essentially the same components at this point, or some subset of those components, just configured in different ways. So if we can get it down to the basics of what we're trying to do and how we're trying to run these things, then I think that we'll make some progress in this unification effort. Here, I wanted to talk about the big three apps. I call them the big three, above the line here with medium range weather, short range weather, and the hurricane application. Each of those three have kind of paved the way into operations. We've seen a couple of the rainbow diagrams so far. And the cool thing about these three is that they are meeting the NCO standards as kind of outlined in their design. And that helps us to be able to find the commonalities between these big three workflows that are going to allow us to apply some pretty straightforward software concepts when we're going to do this unification. But these aren't the only three that we're after at this point. We think that there are lots of ways to expand what we're doing here into a variety of the other applications that are out there. Typically, I have these come in one at a time, but PDFs, man. Okay, so we're talking land EA or reforecast and reanalysis. We've had conversations about subseasonal to seasonal exascale prototypes, and I'll talk a little bit more about that. And that just means running across a variety of platforms instead of just one. Atmospheric rivers, total coastal water. All of these things are using those same components at their core. And then even as giving this talk multiple times in multiple different venues, I've learned that it extends even past this and past UFS to the entire NWP community, so that we're not just roping ourselves into solving problems that we have, but as a broader community of folks not necessarily using those UFS components right now, we can be solving similar problems. And having the conversations about where that collaboration can happen is key. So I mentioned that they're all following, or the big three are following this operational standard that NCO has laid out. That just means that we have this kind of tiered approach where we have some configuration layer that sets up an interface to a workflow manager. The workflow manager here could be any of a variety of third-party managers that we have. And then that manager is typically going to interact with the batch system on your HPC. Then you have some run scripts that are, some people call them run scripts. I've been calling them drivers a lot of times, that are going to run those components that you want in your workflow. Those you might call other utility scripts, but they're all essentially going to call some compiled executable or piece of code in the end. So that could be the UFS weather model, it could be UPP, or any variety of other executables. Now, because we have that structure in those particular apps, we can use those to start to see where the modularization, portability, and robustness can come from when we are trying to exercise our vision here. We want to take a services-based approach to ensure that we can have extensibility and usability from all the UFS applications. Now, we've had a lot of conversations about what services-based means here, but here I'm talking about an architectural design of a single-use tool that does a thing, and it communicates with another single-use tool in a very similar way as all the other tools. This does not mean that we're going to be running this software on the internet and that you'll have access to that. We also do want to develop a user interface, and that comes into that configuration layer that I talked about on the previous slide. And that's a space where the UFS community can really come to this thing and be comfortable using it in a variety of configurations that we've been hearing about in all of the other sessions. We do have some team goals, of course. Obtain more funding is at the top. We've been working on that, and I think we've made some progress. I'm hoping that as we continue through the process in an iterative design approach, we can ensure that we have more buy-in from NOAA leadership over time as we're delivering useful tools. And then to do that, we'll regularly need to release those tools. And of course, all along the way, we'll be applying software best practices. Making sure that our code is well tested and easy to use in the toolbox, and then extending that into a framework over time. So in the upcoming planning increments, and this is a piece of development time in the scaled agile framework that EPIC uses to kind of manage what we're doing. That's a 10 to 12 week period of development. So over the next 10 to 20 weeks or so, you'll start to see more standalone tools come out of our development process. And then we're really hoping that early on, then those tools can iterate and make sure that we're solving the right problems, essentially, and doing it in a way that's useful for the end users. In the medium term, so the upcoming year or so, we're going to start looking at how to get that framework really transitioned to the service-oriented architecture that I mentioned earlier, so that we're starting to feel more like a plug-and-play environment. So if you want to drop in a new whatever piece of your workflow, you can. And then in the long term, we can start to apply a strangler pattern to gradually start replacing each of those existing components with the newer service-oriented architecture replacement. So the idea of this strategy is to unify gradually, iterate often, and add value as soon as we possibly can. Now, we've had a lot of conversations about how we're going to prioritize this work, and this is just a basic example, and over the course of the last couple months even, this has grown, and I appreciate that because it really shows that we are all in here targeting the same types of things. But in this example, I'm showing how we can bring EPIC goals, JTTI goals, and SENA goals all together and start to identify which tools are going to add the most value as soon as we possibly can. So in this example, I'm saying that EPIC is supporting HAFS coming up, where HAFS at the very basic level is a real-time 6-hourly cycled ocean-coupled limited area model with moving nests. JTTI, on the other hand, is all about supporting a short-range weather and a transition from GSI to JEDI in that particular contract. So in that space, we're talking about SRW or Rufus supporting a real-time hourly cycled limited area model with stationary domains. So there are similarities and differences in the way those are configured. And then with our software engineering for novel architecture experiment, we would like to be running a very prototype version of the 3D ENVAR limited area model with ensemble members that are run on a variety of different platforms. So if we start to look at what each of these has in its workflow, then we can start to identify that, you know, they're each running UFS as a forecast, they're each using GSI as a driver, a GSI as a data assimilation, and then they're all making initial conditions or lateral boundary conditions from global forecast. So all of these things are common. Those are the ones that we're going to aim at first. Other common tools that are necessary are the interfaces to some of the workflow components. I do want to highlight a couple of the standalone tools. This is where we have started to really get into the space of, oh, I need that too, and having some collaboration here. So configuration management tools are already out there and released. We are in the process of that iterative design approach so that we've completely revamped our entire repository since these were released just a couple months ago to introduce Conda packaging, and we are up to 100% code coverage on our testing, but these are the same tools that we're using here. So here we are talking about how we can start to introduce a single YAML interface, or JSON if you like that, any of the common different markdown languages that you might be used to. Having a single interface like that to your entire workflow can be achieved with these two tools. And that takes into account any of these name list type files, or the files that you might need to template because they don't necessarily follow a standard format. So each of these then can be handled with these two tools in a way that allows you to configure, say, the 10 different types of parameter files that you have for the UFS model. But that also applies to other components like GSI using nameless or a variety of other things. And then a second one includes how we interface to ECFlow and Recodo, because those are two of the workflow managers that we want to interface with here. So essentially, how can we most flexibly define our workflows? Using a YAML configuration is one of the ways that we can do that. We process all of that information about how we want to define our workflows in terms of the resources they need and the dependencies they have, and then create that XML file if you're working with Recodo, or those ECFlow suite definitions and job cards. And then a file mover is one that has gotten a lot of attention in several different groups that I've given this talk to, and I'd like to hear your thoughts as well. But the idea that we have data everywhere, and we don't always know where to go get it. If we can pair a file mover that knows how to get it from wherever it is to where we need it, and also know where it is, then we're starting to get into a space of having a single user interface that is helpful in a lot of ways where we may not have access, or we may not know how to interact with cloud block storage in certain ways. All of this is just generally aimed at lowering the learning curve for folks who want to get into running a numerical weather prediction system that is UFS, or maybe even other opportunities. So obviously this file mover would be agnostic to whatever model you're running. You just need to know where the data is. I do want to invite you all to stay in the loop in this conversation. I know we're probably going to get cut on questions here, but please do reach out. Jillian mentioned earlier that we have GitHub discussions and issue options. We have that too here in Workflow Tools, and I invite you to come to that conversation. Reach out anytime to me if you have ideas about how you might want to incorporate these tools. But we do also have read the docs for contributors and users to start using these tools as they currently are. So that's all I have. Thank you.
Okay, thank you very much to all the presenters. So we're going to take a break, and then we're going to come back for a joint Q&A session. Thank you very much.